last 2 years. This is divided into 2 pillars, knowledge production and outreach. So on the knowledge side, we released at the last IRENA Innovation Week, 2 years back, September 2018, our first report on hydrogen from renewable power, where we set a bit the scene. And well, from that day to today, we came pretty a long way in terms of hydrogen globally. The discourse, the announcements, the policies have been quite rapidly expanding. So we had an update with new insights 1 year ago at the Hydrogen Energy Ministerial in Japan. And then, as Dolph mentioned, we released Reaching Zero with Renewables 21st of September. And we are in the process of finalizing a report on electrolysers, which I will give you a couple of insights only today. And in terms of outreach, well, we started with a session like we have today. We had a first session on hydrogen and innovation week 2 years ago. We had some thematic meeting in our governing bodies that culminated with a ministerial roundtable in January this year, where CEOs and ministers discussed the issue and the challenges as well as the solutions on how to scale up hydrogen for decarbonization. And from that experience, ministers asked us to continue the dialogue. And because of that, we established a collaborative framework on green hydrogen in June 2020. And we are now opening this up to participants from private sector, academia, other partner organizations, and so on. So we're making that a very open platform. So this is happening as we speak. And of course, this is an ongoing effort. Next slide, please. So from a more quantitative perspective, setting the scene. So these are the combination of the insights from the latest global renewables outlook and the freshly released Reaching Zero with Renewables. Point of this chart is that we need a set of solutions through renewables, energy efficiency, and hydrogen as a role to play in getting to zero. So increasingly, the message here is that the closer we get to zero, the more we will need to produce hydrogen derivatives to be able to decarbonize the so-called hard to decarbonize sectors. Next slide, please. Just a quick overview on the challenge in terms of the economics of hydrogen. So today, with some of the best renewable resources, let's say $40 a megawatt hour, and current cost of electrolysers, in some places we see better prices already today. This is from 1 year ago. We are still at about $3.50 a kilogram, which doesn't make it competitive with alternatives from fossil fuels. However, with the cheapest renewable resources we're seeing today, and this has improved also over the last year, so $20 a megawatt hour, we've seen auctions at 15 and below these days, but from $20 and below, it starts to get very interesting. So what do we need next to really get to a very strong, compelling economic case for green hydrogen is to reduce the cost of electrolyzers. So we have a moonshot there. So the best we guess we can get to in the next few years or a few decades, probably, which is $200 a kilowatt in combination with the best renewable resources will get us extremely competitive with alternatives, including blue hydrogen from fossil fuel with CCS. And this essentially means that the combination of renewables and electrolysis is what can get us there. Next slide, please. So just to give a bit of a perspective of how important is electricity price. So in this case, we fixed the cost of electrolyzers to a very ambitious target. We are not there yet, but we have estimates that we might be able to get there in a decade, which is fairly good given the pathway to get to zero requires hydrogen to come up to speed in the next decade. And then this is the challenge we're trying to tackle today, how to get from zero to a very significant market in 10 years by 2030. So in this case, you can see that cheap electricity is a prerequisite to get to a competitive hydrogen level. So to go below 2, the only chance is to get at least $20 a megawatt hour and below price of electricity. So only the biggest large renewable resources can achieve that. Next click, please. Less sensitive, but assuming we have this $20 a megawatt hour, Then what we need to do is to further reduce the cost of electrolyzers to get below $2 and to get quite well into the territory of blue hydrogen and other alternatives. And what you see here is that it is less sensitive than electricity, but it's equally important to scale up the production of green hydrogen through more affordable electrolysis. Next slide, please. So this is our forthcoming report on the subject. So for those of you that are not familiar with electrolyzers, essentially these are machines that can split water into hydrogen and oxygen. Very well established technology. The idea there is that this has been deployed for over a century for different purposes, then producing green hydrogen for energy use. So what we're doing as we speak is to essentially track projects that go from few kilowatts or hundreds of kilowatts a few years back, with few exceptions, now with announcement moving from hundreds of megawatts to gigawatt scale, and we're hearing new announcements every day, and more of these are reaching the gigawatt scale. So what do we need to do in parallel is to get R&D to essentially give us the next generation of electrolyzers while we scale up what we have today, which is already quite good. And you will hear from our excellent panel to discuss that in a minute. So two key points, I think trade-offs are very important. Durability, efficiency, and cost have a trade-off. If you make it more durable, you might end up making the electrolyzer less efficient. And overall, you need to balance this to get the minimum cost of hydrogen, which is the objective. And of course, an electrolyzer is can be looked at from the perspective of a cell or can be looked at a plant. And so when we look at a plant, there is more than just the electrolyzer stack inside the plant. There's much more. Again, our panel will talk about it, but I will also have one slide about this. And so we need some innovation also, as we're in Innovation Week, looking at membrane thickness, the type of catalyst that we're using, and the amount of catalyst that we're using, the coatings, the electrodes. So it gets very easily quite technical. And one point there is that we really need to look at materials, because some materials that we're using are very scarce. And as we scale them up, orders of magnitude, that is what we need, then we might have some bottlenecks along the way in the supply chain. Next slide, please. So this is, in brief, a very simplified view of an electrolysis plant. So you have the stack, you have electricity from renewables coming in, you need a transformer, you need a rectifier, and then out of the stack you get the hydrogen and the oxygen, and you need to compress it and clean it and feed it into your either pipeline or storage tank or trailers or ships. It really depends. And of course you need feed water supply. This is not an issue where there is even seawater. Even if we consider desalination, it's not a major expense, yet it has to be a significant volume of water accessed for being able to produce hydrogen at scale. The cost is about 50-50 between the balance of plant and stack components, with different potential for cost reduction. Next, please. So the balance of plant, essentially, there is a significant scope for reducing the cost of power supply. This is power electronics, so we've seen a dramatic reduction for solar PV. We will probably see the same here. Next, please. The core of the plant is the cell stack, and this is where it gets quite technical on electrochemistry. Important to note there is that we have several components, and so parts like bipolar plates, which are not very well known outside of the industry, of course, take a significant part of the cost. Next, please. And then the very core, the catalyst-coated membrane, is where we see materials like iridium and platinum, and here I'm talking about PEM, just to make one practical example. This is where the rare materials are typically situated, and this is where some potential cost reduction can be tackled, but this is yet 25% of the stack, and so about 10% of the total of the plant. Next, please. So let me conclude with what I mentioned at the very beginning. We established a collaborative framework on green hydrogen based on the call at the 10th assembly from our members to continue the dialogue between public and private sector. We have an excellent dialogue set up for today as well. So the idea is that this is very much appreciated by governments to get insights and views and perspectives from private sector on how to scale up, and at the same time suggestions on how to make policies and regulations align with the objectives that we are seeing coming up in more and more hydrogen policies around the world. We have a few elements that have been identified as priority: the knowledge sharing, collaboration with hydrogen initiatives, and we're very pleased to collaborate for the time being already with IPHE and the Hydrogen Council, which respectively would be moderating the next session, and they are partners for the session and the next keynote today. The nexus between hydrogen and renewables is clearly IRENA's mandate, and of course, knowledge about all steps of getting hydrogen from production to consumption are very important, as well as standards and regulatory framework and best practices. And with this, next slide, please. I conclude my presentation. Thank you very much for your attention, and I look forward to the discussion to follow.
Thank you very much, Emanuele. I thought that was very clear, and I hope people got a good sense of the topics that we are talking about here today, in particular the critical importance of driving down the cost of electrolyzers as part of driving down the cost of green hydrogen production. So we are going to dive into that topic in our next panel. We have an excellent lineup of speakers who, between them, have a wide range of expertise on the topic. This next panel is called Electrolysers Production. It's moderated by Tim Carlson. Tim is Executive Director of the International Partnership for the Hydrogen Economy, IPHE. So Tim, can I hand over to you, and can I ask all the panelists to please turn on their cameras, and Tim will introduce you. Tim, over to you.
That's great. Thank you very much, Paul. As Paul said, I'm the Executive Director of the International Partnership for Hydrogen and Fuel Cells in the Economy, the IPHE Secretariat, and it's my pleasure to moderate the panel on electrolysis production, electrolysis for green hydrogen production. As Paul suggested, please send in questions via the chat or the Q&A panel, and hopefully we'll have time very much to address some of those questions. I'm going to provide a brief bio introduction. I understand the material is also available on the site, I think, but and then we'll walk through each of the presentations and then do Q&As at the end. So with that, I'd like to introduce our first panelist, Professor Armin Schlettler of Siemens Energy. Armin is the Executive Vice President of the New Energy Business at Siemens Energy, as well as the President of the German Association for Electronic and Information Technologies. Prior to that, prior to being at Siemens, Armin had several positions at ABB and in their business area of high voltage products and substations. Armin, you have the virtual floor.
Emmanuel, for your excellent introduction, which I very much appreciated. Maybe if you just switch in order to keep the time to the next slide, because the first thing, if you are talking about the electrolyzer as a product, as a system, we need to look for what is required in the market, right? And what we do see right now, I mean, not talking about the regulation and decarbonization commitments, but on the right-hand side, what we see in the market is that there are a couple of different market segments. The smaller ones where typically you start, but at the end of the day, we see more and more trend towards large or bulk size electrolyzer systems or plants. And we are talking about plants, not single stacks or electrolyzers. So we're seeing for the mobility and the fueling station, say for hub stations, we see in the range of 10 to 20 megawatt electrical demand. For smaller industrial applications or for first, say, larger pilot projects, the 100 megawatt class is now popping up, where we see a market in the range of 150 to 250 megawatt applications. And then for bulk industry, large steel refineries, etc. And of course, for the export business, synthetic fuels and methanol, ammonia, we see the gigawatt range. Interesting to know that at least for our technologies, we are focusing on the PEM technologies, a proton exchange membrane. We see a clear trend towards the bigger ones, which is, I mean, every 4 to 5 years, we get an increase in the project sizes by a factor of 10. 2015, we had the 1 megawatt class. Last year, we implemented, say, the double-digit megawatt class in operation. And we are in firm bids and discussion and announcements and MOUs already signed for the 100 megawatt class. So this is something, a clear trend, and which is following exactly what Emmanuel said before. Maybe it's the next slide. When we are talking about electrolyzers, we need to be careful. It's not the electrolyzer, as Emmanuel showed before, and actually it is not even bringing capex down. At given, and in some or many areas of the world, electricity prices are already below $20 per megawatt hour of green electricity. At given high loading factors, say operating hours, the capex is not that important. I mean, it is, of course, important for the investment, but what we are focusing on is the balance of plants. It is safety, security, availability, and serviceability. So talking about levelized cost of hydrogen or total cost of ownership. This is, to my understanding and our understanding, more important rather than just focusing on capex of an electrolyzer stack. Right. So what we are focusing on and what we are doing at Siemens Energy, I mean, just recently getting listed in the German stock exchange here, is from planning, consulting, and design towards the renewable integration, say wind and PV, the grid connection, the electrolyzer itself. I mean, as an electrochemical plant, the auxiliaries, which has been mentioned here as balance of plant or EBOP, if you're talking about the electrical part. In the later sessions, we will talk about ammonia, and then we have, of course, the next stage, right? How to supply the nitrogen, how to supply maybe the CO2 and get the carbon monoxide out of that, and then the synthesis. So we partner for that. We are quite strong in the center here, and this is really where our focus of our business is. Maybe last slide. Two parts why we believe, and our customers believe as well, why we are a valuable partner. This is maybe the sales pitch, right? Necessarily required here. We have right from the beginning focused on industrial scale electrolyzer systems and plants. Although there is not really a standard in the market, I mean, we get requests for, say, 10 and 5 and 15 and 20 and 50 and 150 megawatt ranges. We need to be careful that we do not over-engineer everything and reinvent the wheel all the time. So what we are doing is we have pre-engineered and prefabricated packages. And if you would like to get, say, 100 megawatt, then it is 2 times 50, because 50 megawatt is pre-engineered. We have the basic engineering, etc. And the next one, of course, the gigawatt range is somehow different. Of course, then we should, and we do it in a slightly different way. So this is important. And the final topic I would like to mention here before stopping is, in order to reduce the overall cost over, say, 10, 15, 20, and 25 and more years of operation, you need to have a digital twin of the electrolyzer, of the system, in order to operate the overall plant, depending on the input factors, which is, of course, availability of low electricity prices, the expected output in the, say, hydrogen demand in, say, tons at the given, say, expected price or cost, and, of course, maintenance and service intervals you need to consider here, because availability is key. We don't need to talk about, I guess, safety and security. This must be given. So what we do is we focus on large, we focus on prefabricated, pre-engineered packages and the full value chain, say from electricity production, renewable, of course, for green, and until, I mean, the synthesis later on with partners, and the digital services, we call it the digital twin of the plant and of operation, is key for the reduction of total cost of ownership. That's all. Should be enough for the input statement. I'm looking forward to the other presentations and our discussion. Thank you.
That was great. Thank you very much, Armin, for a very succinct presentation and flagging the role of the balance of plant, and to avoid the over-engineering and the way to get multiples of what we know to do in place. The next panelist I'd like to introduce is Dr. Ichi Ohira, the Director General of the New Energy and Industrial Technology Development Organization, NATO, their fuel cell and hydrogen group within the Advanced Battery and Hydrogen Technology Department. Ohira-san is responsible for the overall strategy, execution, and coordination of NATO's research and development and demonstration projects on fuel cells and hydrogen. He's coordinated fuel cells and hydrogen activities with the international stakeholders, the IEA, through their technology collaboration programs, and also with the IPHE as well. Ohira-san, you have the floor.
Okay. And thank you, Tim, for your kind introduction. I'm very happy to join the IRENA Innovation Week to deliver our kind of activity in the past 2 years. Well, unfortunately, Japan is just behind the European activity in the past 2 years, but we try to best effort to catch up to your activities. Next, please. Well, NATO is not manufactured. We just have the funding agency to promote the national R&D program. And so this is our strategy, or we have the 3 pillars to promote the R&D in the past years. One is in the R&D or electrolysis itself. The second one, and we utilize in the electrolysis and the layer field. So it's been the past years demonstration project. Well, and the fundamental the scientific approaches should be needed to understand what's going on at the inside of the electrolysis through the upgrading the technologies. So next, please. So next, please. Okay. This is an approach. The fundamental research is to understand what the inside of the to reaction of the electrolysis. We did several approaches. One is the electrode, electrolyte interface analysis, observation, bubble behavior, accelerate degradation protocol, reverse current behavior analysis should be important for us. We integrated this kind of analysis technology to develop the kind of the platform to understand the electricity itself, and we feedback this information to the material or CCM development. Well, next, please. This is our approach for developing the electrolysis technology. And now we are focusing on the alkaline electrolysis and the PEM electrolysis in the short term. And the top slide shows the Asahi cascades, the large-scale alkaline electrolysis, and 3 square meter wide and 1 stack. And you may see the light graph, and the top of the blue line is input from the wind turbine. And bottom red graph, it shows the cell voltage at the alkaline electrolysis. You may see and the good following, good load following, good response, and even in an alkaline electrolysis. So we decided to utilize this alkaline electrolysis on the particle gas systems. And the bottom photo shows our new technology for hydrocarbon membrane for electrolysis developed by Toray Corporation. And the middle of the graph, you may understand is a good performance compared to the Nafion as a current PEM to membranes. And after 225 kilowatt test, and we going to move to the scaling up as technology. Next, please. Now we NATO have been conducting the 2 type of the large megawatt class particle gas project. And first, we started the kilowatt class around that 25 2015, and after to closing the project, we moved to the megawatt class. And left figure showed our part gas project at the Fukushima Prefecture. We introduced in the 10 megawatt alkali water electrolysis with a 20 megawatt PBOY. And we try to produce some kind of green hydrogen, and also to provide in the grid balancing with the dynamic operation of the water electrolysis. Our first plant, it provided green hydrogen to the Tokyo Olympic Games in this year, but unfortunately it's postponed in 2021. Maybe I'm happy to introduce this technology for maybe the next year Tokyo Games. And later on, and we also developed the 1.5 megawatt water PEM water electrolysis part gas plant, and we utilize a large scale metal hydride to hydrogen storage combined with compressed hydrogen storage. Okay, next please. But we recognize that a lot of challenge to realize the part gas for electrolysis technologies. We need to improve the electrolysis technology itself. We, Japan, have the target for future target to cost target and efficiency target to the 2030. We need to improve the efficiency, durability, because under the dynamic operation condition, it's very close to the part gas conditions. And the performance, lower performance, increasing the hot cold start, lamp rate, response speed. Scaling up should be important. Well, and next step in the novel material to reduce the cost or to increasing the efficiency should be required. And the part gas is a kind of a developing system technologies. We, Japan, try to be commercialized this system by around 2032. We think about total system optimization, including the balance of plant. Well, and they also developed the energy management technologies we based on the several data for weather forecast and market condition, etc., etc. Well, operation or maintenance, yes, maintenance cost is a big part of the hydrogen cost. We try to make it reduce to the maintenance cost or operation cost. Okay, most of the important in the business model to market mechanisms. We didn't have any market model in Japan, so we try to develop this kind of model. Okay, thank you very much.
Okay, thank you very much, Ohira-san. That was very interesting, and it's great to see the progress at the Fukushima Prefecture on renewable energy and the technologies around that. That was great to see. So thank you very much. Our next speaker is Thorsten Herbert. Thorsten is the Director of Market Development of Public Affairs at Nel. He recently joined Nel in that position and represents the company at various European associations, organizations, and forums. He has been part of the hydrogen industry space for more than 18 years now, building the industry in Germany and working many years at General Motors, and then more recently at NOW, the main funding arm in Germany for alternative fuels. Thorsten, you have the virtual floor.
Thanks a lot, Tim, for the introduction. Thanks a lot for the great presentations before. And actually, the content I prepared fits quite well, since let's say the previous presentations very much went into some technical details. I would actually love to also look at the political arena and what is going on in Europe at the moment, and what that means also for our industry. Next slide. Yeah, of course, a short introduction of Nel, then 2 highlights with regards also what are we doing to advance our technology and what can we actually do ourselves as a technology supplier to advance the technology. And then, as mentioned before, I would like to shed a light at the European momentum that is rolling at the moment. Okay, next slide. And yeah, next. Yeah, so you could actually say Nel is green hydrogen. We are a pure play hydrogen technology company with a global footprint. So our manufacturing facilities are located in Norway, in Denmark, and in the US. Of course, this comes with a global sales network. We are the largest electrolyzer manufacturer with more than 3,500 units delivered in a lot of countries, and that already since let's say, over 90 years, which is quite remarkable, we think. In addition to that, we are also like in the lucky position that we comprise also another part of the supply chain as one of our products, being the hydrogen refueling stations, where we also sold more than 80 stations already in more than 9 countries. Next slide. Looking into the manufacturing facilities and also pointing out already one very interesting fact, because if you look at the PEM electrolysers, we are now in the US with 40 megawatts per year capacity. But the highlight, and I will dive a bit deeper into that in one of the later slides, we are actually now preparing the plant in Norway to be capable to for an output of 500 megawatt per year by end of next year. So this is currently in the process. And also a very good perspective is that this location here, which we also see on the picture, is already now capable also to be expanded to 2 gigawatts per year just by quadrupling the equipment here. And then the refueling stations in Denmark, we are ready to build up to 300 stations a year. Next slide. So 2 latest developments. Again, I think one highlight for us, and that also leads me to one comment to one of the earlier presentations. I think the introduction of Emanuele, looking at the scenario with $350 per kilowatt, really with the perspective to have this huge capacity and also the fully automated manufacturing principles here in place already soon. We just lately, in our latest deal, we already sold our alkaline technology in this price range. So really, if we really anticipate what we can gain from this upscaling in manufacturing capacity, we are already there. As I said, this will start test production mid of next year and will be ready for the whole capacity end of next year. And as I said, just by multiplying the lines, we would be able at this location to also ramp up to 2 gigawatts per year. Next slide. Looking into the technology, and there lately we got some key R&D grants newly granted, 2 quite large ones for our looking into our R&D activities, and actually addressing both technology we are offering. On the one side, the alkaline electrolyzer. So we have a R&D grant here in Norway, improving the next-gen alkaline electrolyzer also at pressure. And then on the US side, a quite significant grant also to develop further our PEM technology with regards to components, manufacturing methods, but also optimizing flow and conductivity of the stack. Next slide and next slide. Quickly looking into the European momentum. So I think you're all aware that beginning of July, the European Commission came up with this very ambitious strategy. We are talking 40 gigawatts installed electrolysis capacity in 2030, but already 6 gigawatts in 2024. And this is actually, and that is one of my messages I want to bring across, this should be our main target. So we should, in Europe now, really focus on this 6 gigawatt in 2024 and come up with a roadmap. What we need to do, what do we need with regards to policy measures, and looking into the next slide. We already see not only on the Commission side with the 40 gigawatts target, but also like ambitious targets of the member states. But still here we are like roughly at half of this 40 gigawatt, what the member states pledge so far. One other thing before I come to the end is that obviously, and I put the logos here, we already have funding mechanisms in place to come to this milestone of 6 gigawatt by 2024. But I think the key, and this is here in my subtitle, I mentioned it, the key now is really that we as an industry cooperate, that we coordinate ourselves, coordinate each other to, in the most efficient way, utilize these funding schemes and also address the additional needs we have. Next slide and last slide. That is actually possible now in Europe, and we now just, our CEO got elected into the board of Hydrogen Europe. So join these initiatives, join the European Clean Hydrogen Alliance. This, as of the European Hydrogen Strategy, is supposed to be the main vehicle, the main body to coordinate the implementation of the European Hydrogen Strategy. One last message in the direction of the European Commission: we really need to proceed now in the European Clean Hydrogen Alliance. The industry is ready. Already 300 organizations have signed up for the European Clean Hydrogen Alliance. The industry is ready to come up with a project pipeline, to come up with recommendations and a roadmap. We just need, let's say, the next steps and the facilitation by the Commission now. Thanks a lot.
Okay, great. Thanks very much for that, Thorsten. Very interesting presentation, and I think it gives an example in a region, the scale and scope of the opportunity, but also the challenge ahead and parts of how that can be addressed. So thank you very much. That was a great presentation. I'd like to move on then to our next presenter, and that is Denny Thomas. Denny is leading the business development group of the activities for water electrolysis at Cummins, which acquired the activities of Hydrogenics in 2019. Denny represents Cummins in several EU associations, including Hydrogen Europe and Win Europe and other organizations there that are looking to hydrogen as to play a significant role. He is also, as I know, a mainstay in hydrogen-related policy discussions across Europe. So, Denny, please, you have the floor.
Hello, I hope you can hear me well. Good morning from Brussels. I hope you are all safe wherever you are. It's a pleasure to speak to you this morning about large-scale PEM water electrolysis. And I would like to give you an insight about the current status of the technology and a little bit the way forward. Next slide, please. First of all, I need to make some introduction because Hydrogenics was well known in the field of hydrogen. But Cummins is, I would say, the new kid on the block in hydrogen. And Cummins is, in fact, a large company. It's a large US company with more than 100 years of history in the field of energy, and mainly in the field of combustion engines, diesel and gas engines, both for the mobility sector and the stationary power generation. And obviously, due to climate change and the energy transition, Cummins has decided to diversify its technology and has entered into electrification technologies already in 2018. And in 2019, there were several acquisitions in the field of hydrogen and fuel cells. Cummins, it's more than 6,000 employees all over the world and a presence in more than 190 countries. Next slide, please. The activities of Cummins in the field of hydrogen, they are quite wide. We have technologies in the field of electrolysis. I will present them in a minute. We have also technologies in the field of fuel cells, and also we have technologies in the field of hydrogen storage tank. And the idea is to be able to offer complete systems, both on the electrolyzer side and on the fuel cell powertrains for mobility. And among those acquisitions, there was the acquisition of Hydrogenics, which was the major one, including electrolysis and PEM fuel cells. There was also, a couple of years ago, the acquisition of the solid oxide fuel cells of General Electric. And then there is a joint venture with NPROX in Germany on the hydrogen storage tanks. And the aim is really to be top performer in the industrial hydrogen generation, but also in power to X. And I think that's the focus of today's discussion. And on the mobility side, our focus is mainly on mobility and heavy duty mobility, like trucks, trains, buses, etc. Next slide, please. Concerning electrolysis, we are one of the few companies having different technologies in electrolysis. Alkaline, we've been active for more than 30 years in that space. As you can see on the product table, and I know that a lot of you, they like the numbers, and that's why I've included that slide in my presentation. At Cummins, our alkaline technology is more in the kilowatt scale, because we use pressurized technology up to 10 bar with a possibility to increase it up to 27 bar. And our biggest product is in the range of half a megawatt with a production output of 100 normal cubic meter of hydrogen per hour. And the philosophy on those products has been always to deliver turnkey systems, including all the utilities and a kind of a plug and play design. On the PEM technology, which is really the focus of my presentation today, we've been developing this technology for over the last 10-15 years. We have already commercial products at 2.5 megawatts, which is again containerized systems. And we are in fact currently developing our product towards the 5 megawatt and bigger. And in this case, we will not follow the containerized systems turnkey, because we believe that for a bigger project, there is a need to integrate those technologies in a much more complex systems. And so we are partnering with a lot of EPC companies, because we think that they can bring a lot of value and know-how also, and they can bring a lot of cost savings in the cost of large-scale systems. Next slide, please. Obviously, the building block that we use for the PEM technology is a PEM cell stack with cells with a surface area of 1,500 square centimeters. What you see here is a 1.25 megawatt cell stack, which can also operate up to 1.5 megawatts. And that's the building block of the current commercial product. Next slide, please. Using that building block, this is the type of systems that we can deliver today on a commercial basis, between 1 megawatt and 2.5 megawatts, by just playing with the number of stacks that we use in that system. Obviously, one important word when we speak about cost reduction is standardization. Obviously, that's something that we are developing right now. It's really to make sure that we use standard platforms that will allow us to reduce the cost on the long term by getting into large volumes. Next slide, please. Concerning this technology, it has been already deployed in a number of sites. We have more than 15 projects in the megawatt scale range for various types of application and in various geographies. But you see some of those pictures here. Next slide, please. And concerning the current development, we are upscaling our building block. So the 1.25 megawatt cell stack, we are doubling its capacity by doubling the amount of cells. And obviously, by doing that, you don't double the cost. And in our, I would say, general philosophy at Cummins is bigger is cheaper. And that's what we will follow also on the what we call the balance of stack and the balance of plant. Obviously, by doing that iteration, we have a building block which will have a 2.5 megawatt, which is interesting for megawatt scale type of projects. Again, we are also at the very, let's say, initial phase of the learning curve on PEM technology. So we still see a large potential for a cost reduction with this technology. Concerning the efficiency, I've presented in the table of products the numbers of efficiency. And I think this was also related to some of the questions in the chat. How do you compare efficiencies? And I think it is really important that each time you mention this, that you refer to what you're actually discussing in terms of scope of supply. Concerning the PEM technology, it is very suited actually to connect it directly with wind or with solar energy, because it has the ability to react very fast to a dynamic operation in terms of seconds, and with a very wide operating window. And also it is very compact, and it has a lot of benefits in terms of maintenance, especially because we don't use a KOH, which is the case for alkaline technologies. And finally, with this technology, we can deliver systems with a 30 bar output pressure, which is quite interesting when you want to make power to gas systems, or if you want to inject the hydrogen into industrial processes. Next slide, please. Using this 2.5 megawatts building block, actually, we have developed today this product, which is the electrolyser 1000. And that's a 5 megawatt product integrating 2 stacks of 2.5 megawatts. And what you see here is really the standard and modular solution that we offer today, which is including all the heat exchanger, the water polishing system, the gas liquid separators. It is an indoor system, but to also allow safe operation, we have enclosed all the sensitive areas where there is hydrogen generation. Next slide. And this product is currently being deployed in a project in Canada together with Air Liquide in a 20 megawatt setup. And so you see here on the right side of the picture, this 20 megawatt project, which is made out of 4 systems of 5 megawatt, each of them connected to one rectifier. And that's typically the type of scope of supply that we would see for Cummins in the future. And then all the rest of the plant, meaning all the water purification system, the cooling of the systems, and all the medium voltage, that's something that can be done by an EPC, a local EPC, that can actually lower the cost of the complete system. And so you see that our focus is really to make sure that the red items, that we can deliver them at the lowest cost, but also guaranteeing all the safety and quality requirements of those systems. And so this project in Canada is actually in the phase of commissioning. And obviously, as soon as it will be up and running completely under commercial conditions, there will be quite a lot of communication from our side. Next slide, please. So to conclude, what I want you to remember is that bigger is cheaper. That's what we think. We are today validating this 20 megawatt, I would say, project, which will be the basis for projects up to 100 megawatts. But if we want to be able to deliver gigawatts, we will need to make a next iteration into our products. And for us, it will go through bigger stacks, so even more than the 2.5 megawatts. Also bigger systems, so having more stacks sharing the same balance of stack, and obviously standardization and partnering with EPC companies. Thank you for your attention.
Okay, great. Thank you very much for that, Denis. Very informative presentation, and it was great to see Cummins step into this space. I think that sent a very strong signal, and picking up a Canadian company, the Hydrogenics, was a great mark for them as well as an indicator of leadership in the space. So thank you very much for that presentation. That was great. Our next presentation will be from Jan Justus Schmidt, the co-founder of Enapter. Jan was listed in Forbes 30 under 30 in energy in 2020. Since co-founding Enapter in 2017, Jan leads the technical development and oversees the business operations of the company in Germany and Italy. He holds a master's degree in aerospace engineering from Sheffield in the UK, University of Sheffield in the UK, and an MBA from Hong Kong University of Science and Technology. And with that, Jan, the floor is yours.
Thank you very much. So I'm very happy for this opportunity to present our AEM electrolyzers and Enapter's very different approach to the hydrogen world here with you. The challenge for all of us is to reduce the cost of green hydrogen to become truly competitive with the fossil fuel alternatives. So we have a very different, we looked at economic history and how the most dramatic cost reductions for technology came about. And what we find is that it is through mass-produced, standardized commodity products. So maybe not always bigger is cheaper, but and we believe that by standardizing commodities, green hydrogen will become cheap. Next slide, please. So at the core, Enapter is an R&D company. Our origins lie with a catalyst development team that was working on non-PGM catalysts, and then developed the foundation of our electrolyzer technology. And today we continue to strongly invest into this path and develop our electrolyzer technology. It's really fun to work at Enapter because our AEM electrolyzer technology is quite young compared to the traditional alkaline and PEM technologies. And so we still see even now a lot of potential for us, untapped potential to further improve it. So on this slide, you can see our current product, the EL 2.1. And we're really proud of this machine. It's been developed over the last 2 years, iteratively developed over the last 2 years. And this machine is now significantly more compact, more efficient, and lower cost than all its predecessors. And we think it has a very strong position in the market with regard to especially to energy efficiency and cost for this type of size of unit. Each EL 2.1 produces 500 normal liters of hydrogen gas per hour, already pressurized at 35 bar. And multiple units of these can just be stacked together to reach any desired production rate that is needed for a project. So why is it that we are building such a relatively small building block, and why can we do this cost effectively? The answer is on the next slide, and it lies in our patented AEM technology. Essentially, the way that the anion exchange membrane electrolyzer works is quite similar to the PEM, but due to the fact that we are working in a slightly alkaline environment, we do not rely on high cost materials. So especially if we remember Emanuele's introduction in the beginning, bipolar plates, we do not need titanium for this. We can just use normal steel. And this is probably even a bigger cost saving than the not having to rely on the PGM metals as well. So we don't need iridium, we don't need platinum, but the biggest cost saving is that we don't need titanium, and we can actually build our stack from very low materials. And then the next feature is that the operation of the cell. Oh, sorry, can you go back to the previous slide? Okay, so we are circulating our liquid electrolyte only on the anode, and we're operating with a differential pressure. That means that on the balance of plant side, for the water circuit, all we need is a tank and a pump, and we are circulating the water through the anode. At atmospheric pressure, we can use plastic components, very low cost. Whereas on the hydrogen side, we are producing hydrogen under pressure, and due to the operation with a dry cathode, actually we are getting highly pure, directly compressed hydrogen directly from the stack. So that means we have both a low-cost stack and a low-cost and very simple balance of plant, and this is the prerequisites for being able to make a building block, a small building block that can be mass-produced. So talking about efficiency, I've included here a polarization curve. Next slide. For everyone to understand the actual underlying details of the performance of the electrolyzer. And so currently, when we are operating at nominal production rate, we run our stacks at 0.8 amps per square centimeter. You cannot directly compare this with other technologies, but within a technology, you always want to improve the current density to be able to have a smaller stack and with less active area to produce the same amount of hydrogen. At our current density of 0.8 amps per square centimeter, we operate at a cell voltage of just over 1.7 volts. And so this leads to a really great stack efficiency. Our balance of plant is so simple that actually also for that only very little energy is needed. And our current system has a steady state power consumption of 4.8 kilowatt hours per normal cubic meter of hydrogen. That's for the complete system. For the stack, it is actually just 4.3 kilowatt hours per normal cubic meter. Next slide, please. Okay, so I've mentioned it in the beginning. We are scaling in a very different way. Rather than building very large individual units, we are building small units that we want to mass produce. So this is, you can draw an analogy to PV panels, for example, or also to the IT industry. In the 1980s, computers were getting bigger and bigger, filling up entire floors and skyscrapers just for a computer for one company. And these mainframes, these big computers, they don't exist anymore. Nowadays, all servers and large computing centers are built up from modular computers, blade computers that are just stacked together. And all of this is based on PC architecture that has replaced these giant machines with modular small commodity items. And so our electrolyzer is the PC of the hydrogen industry. Next slide, please. This is where we are at with our development. So when we started in 2017 until today, we have almost halved the price of our electrolyzer, keeping the size and production rate the same. We are aiming to release a new version of our product every year, making each individual building block smaller, more efficient, and lower cost. So by the time that our mass production facility will be up and running, we think that the cost of our electrolyzers from today will be just 20% of what it costs today. Next slide, please. Stackability is extremely important. So whereas each individual unit we want to make as compact and as compact as possible, we then have to stack them to reach make them very easy to use for any kind of applications. So today, most of our customers put our electrolyzers in cabinets, such as the ones on the left. And we are now working on deploying the first container, building the first container, which has roughly 150 kilowatts. This is just made up of stacking EL 2.1s together. Then the other project that we are working on right now is the AEM multi-core. So when we're looking at large-scale systems, we see that we can benefit both from the cost reductions of the mass-produced electrolyzer building block of the stack, as well as the typical cost reductions that come with centralizing those components that do not scale with unit numbers. So we can centralize the balance of plant for the megawatt scale system. and just put in hundreds of our stack modules, and that can easily be stacked to the right number to the production rate that's needed. And with this kind of system, we will have extremely high reliability. We will have extremely flexible control because each string of modules can be individually controlled. And on the balance of plant, we will have very significant cost savings. Again, looking back at Emanuele's introduction, for example, for the large electrolyzer plant, the balance of plant was 50% and the power supply was 50% of that. So if you're looking at a large electrolyzer, that would mean a quarter of it is just the power supply. Well, with this kind of concept, having modular building blocks that are stacked together, they essentially behave, our stack modules essentially behave like a battery pack. So we can use standardized power electronics that are used also in PV and battery industries. And we can also save a lot of cost on all the different BOP components. Next slide, please. Okay, so with these size systems, we think that we are very well placed to address the hydrogen needs of the energy world of tomorrow. We can see, of course, there will be a need for some very large scale centralized plants for industry and other use cases. But if we look at the scale of European power generation as it will develop, as it's estimated to develop over the next 30 years, we see a very clear trend towards decentralization. We see a big peak at the range, or at the small kilowatt range, which is distributed generation, mostly rooftops and private people, prosumers participating in the energy world. And we see another giant peak with solar, and largely driven by solar and wind, in the low megawatt range. And so looking at these trends of decentralization and smart energy systems in the future, we think that our modular mass-produced electrolyzer is the right way to address this market and to do so in a very flexible manner. Next slide, please. The solar panel has disrupted the electricity world and has made energy consumers into prosumers. And we think that decentralized hydrogen, click one more time, please. And we think that with our modular decentralized electrolyzers, the same can be done to fossil fuels. Thank you very much for your attention, and look forward to the next discussions.
That's great, Jan. Thank you very much for that presentation. When I saw the agenda, I very much look forward to seeing your presentation, given your focus on the small scale and modularize and build up versus some of the others. So that was great that we got the full spectrum of electrolyzers and processes on the panel. So thank you very much for that presentation. I would like to now move forward to the Q&A session with all the panelists. I hope all the panelists are now available. And I have some questions that have come forward, and maybe I can start with a couple, and then we can look and check for some others as well. But a few of them we have, I guess I can start with, we did have a discussion around the efficiencies of electrolyzers, and a question around, there's a number of different versions of, or at least numbers that are out there around what is the efficiencies of the electrolyzers. I wonder if anybody would like to kind of talk in general senses. We heard some of those numbers, but how is there easy comparability, or there's a number of kind of numbers floating around, and I'm wondering if one or more of you would like to just talk about the energy efficiencies of the electrolyzers. Maybe, yeah.
Armin, speak, Tim, is okay?
Perfect. Armin, absolutely. Please.
Okay, thank you. I mean, this is a really good question, and here we need to act on that, because I mean, we need to standardize what we all define, I mean, independent on the vendor, on the supplier, what we define as efficiency. So for the time being, how we do see it is the system, we call it the system efficiency, not stack or plant or whatever, system efficiency, which is the point of common coupling on the AC side. So including transformers, rectifiers, stack, and then of course piping or auxiliaries. So kilogram output of hydrogen based on electrical power on AC side. And this is of course strongly dependent on the current density we are driving. Now, the higher the current density, typically the lower the efficiency overall, the system efficiency. So we could report of say system efficiencies of 80, 84, or even more percent. It's just, you know, by reducing the current density. So typically what we say at rated power, so nameplate power, this is what we define as system efficiency. I would like to get the opinion of my colleagues here in the panel, but here we need to act really something. Otherwise, I mean, we are losing credibility with our customers. So this is absolutely, or actually something I do in my role as the VD president in Germany. Yeah, so try to standardize something, setting up a working group and coming to say figures which are really based on facts.
Yeah, so maybe a few words here. So I'm definitely not in the position to speak for the colleagues from technical divisions here, but I agree that it's a matter of credibility also of the industry that we come up with a joint approach here. So what we typically communicate and what you find on our websites is the stack efficiency. So here we say this is what we with our internal IP and know-how can influence very directly. But yeah, I agree that we need to come up with one joint number or two joint numbers, whatever we think is good, and let's find the right forum where we could discuss that.
Any other comments?
Yes.
I guess, sure, please.
Yes, maybe Tim, but I think there is quite a number of initiatives already ongoing on those topics, and I think it's relevant to mention them here. I know that the Joint Research Center of the European Commission has been working on those topics by developing kind of a common methodology, actually to test electrolyzer equipment and to define also those concepts. So in my view, they are actually extremely clear, and especially when you are discussing multi-megawatt projects, there will be a lot of people looking at those numbers. And actually, obviously, the efficiency, the important number is the one which is experienced by the client, which is obviously the complete plant efficiency. And it could vary quite significantly depending on the type of setup that you want actually to implement in this project. It's also very sensitive to, I would say, what we call the balance of plant and the kind of redundancy level that you want to implement in the balance of plant. So I would say you cannot, at the end of the day, come up with one number. It will be always project dependent. What we can do is that each supplier or vendor needs to make sure that he knows what is the efficiency of the building blocks he's supplying actually to a project. And this will be discussed anyway. What I would strongly encourage is stop working with percentage. There is always the confusion between low heating value and high heating value. That's an old topic. Please use a kilowatt hour per cubic meter or kilowatt hour per kilogram, and then there is no discussion at all on these topics.
Okay. That was my follow-up. Okay, is there some initiative or process underway? But so at least there's one that we know. That's great. Any other comments on this specific question?
I mean, yes, I think that my colleagues have said all the relevant things. Just important. It's really important to stress the importance to say the whole system efficiency, and I also wholeheartedly support the last point from Denise about the percentages. So at Enapter, we always state the complete system efficiencies of the stack plus the balance of plant to together with the definition of the interfaces that the customer has. And we provide efficiency if asked for in percentages, always with the lower heating value to make sure that these values are, very reliable and cannot be attacked. And I think that this is really important to do it in this way. I can say also from a business development point of view, it's a little bit frustrating when somebody brings you a data sheet that says, this stack has 95% efficiency. It doesn't mean anything for the final application. And so, yes, I wholeheartedly agree that we have to communicate this in a very transparent and correct way.
I have maybe last comment, Tim, in this regard, because actually you cannot limit the efficiency of an electrolyzer to one number, because also the efficiency is varying according to the power input that actually you will place to the system. So maybe what the electrolyzer manufacturers could do in the future is actually to communicate about the efficiency curve of their products, and then it will be much more transparent, because actually that's what the projects are asking. That's the efficiency curve, because they want to use our technology in a very dynamic mode with wind and solar. So they are not going to use our technology always at the nominal capacity.
Great. Okay. This obviously is a very, very detailed topic, but it's great to flag those key issues. We do have a couple more questions I want to kind of to get to. One, given the audience, I think it's a global audience, and I know, Thorsten, you and Denny, you've referenced the European situation specifically, but there was a talk of these kind of 40 gigawatt goal, that initial goal for the European Union market. What is the expected demand, or how do you see that? Do you expect more demand than that? What's your, do you have expectations just in Europe at that point? And then is this an opportunity for others as well? This is kind of the open question. Thorsten? Denny?
I can react, I can start. I love this question. It's a crystal ball question. I can say that everyone has been wrong on solar technologies, because solar has beaten all the prognosis from IEA and I think even from IRENA. So actually you are asking us to do the same. What we can tell is that 6 gigawatts by 2024 is a very ambitious target. We see a number of initiatives, I would say in the range of between 5 and 10 megawatts up to 200 megawatts in Europe. Obviously, the main difficulty of those projects is to reach the, I would say, or to pass the financial green light. It means that those projects, they do exist, but they don't have a business case yet, because nobody is willing to pay the green premium for it. So actually, if we really want to see those projects online, we need to make sure that the policy framework is well in place, actually to create the business case for those projects to be realized. And that's a little bit the situation in which we are today. I would say we are on good tracks, because there are a number of say policy instruments that are being put in place in Europe, but there is still quite some work to be done.
Right.
Yeah. So thanks, Dennis, for that. Definitely, with regards to the business case. That's one thing I wanted to mention also during my presentation. So we have some huge, also currently open funding funds here, which are mainly focusing on CapEx. So ETS Innovation Fund maybe as an exemption. Nevertheless, it's really about European-wide levelized framework for these projects. So it's not possible that we talk about exemptions from the EEG levy in Germany, that we talk about hydrogen injection premiums in Portugal. So yeah, we really need to come up with like a joint framework here. And Denise, you already mentioned that This is well understood, I guess. So there is a hydrogen regulatory act envisioned by the Commission, but also what is a fact that this at the moment is slowing down the realization of these projects, and coming and the 2024 target is coming quite close.
Tim, it's Armin speaking here. Because the question was related to, is it the consumption in the European market? Definitely not. I mean, the green molecule market is approximately 50% plus X of the final energy consumption. So the market is huge. It is even higher than the electricity market or electrification market. This 40 gigawatts is an initiative. Actually, it is 2 times 40, right? 40 gigawatt to be produced in say Europe, and 40% to be imported. So it's a good initiative, but as Dennis and Torsten already mentioned, we need to look for the sustainable markets, not relying on subsidies. So business cases are key, and this, of course, will at the end of the day be significantly depending on the implementation of the Renewable Energy Directive 2. In Europe. As soon as this is in place in all the member states, then the demand is huge.
Right. Okay. That's great. Another question that we have that is we haven't the intermittency of renewable energy and the capacity to produce hydrogen. And this question is related to the production of synthetic fuels. So not just the hydrogen, but then moving it on to the production of hydrogen fuels, synthetic fuels. What is the view of the panel for managing intermittency? Do you have views on that particular question?
Shall I start, Armin, here?
Sure.
I mean, when talking about power to X, power to fuels, ammonia, etc., then we are typically talking about bulk generation, and the volatility of bulk generation is not that high. I mean, it is the volatility of solar power, the volatility of wind, which is steeper, but it is relatively easy to predict. I mean, it's a difference if you're talking about one windmill or solar panel, etc. Solar, again, it's more easy. But the higher, the bigger the plants, say the renewable electricity plant, or if you're talking about power purchase agreements, this is not really a big deal. So I do not believe that this will be the key challenge in the future.
Okay.
Yeah,
I might have a different views, or I'd say a different opinion on this, because I think the question is really targeting the lack of flexibility of fuel synthesis, like ammonia synthesis or methanol, which actually need to operate in a kind of continuous mode. So in fact, we see 2 trends. There is the trend of, let's say, greenfield projects directly connected to wind and solar. And where actually this topic of flexibility is key because you have no other source of energy than the wind and solar. So it means that if you are using only solar, you would need to turn down your equipment during the night because there is no energy. And so there we see 2 strategies. One of them is actually to implement hydrogen buffer storage tanks, actually to make sure that you have hydrogen overnight and to keep your synthesis loop ongoing during the night. And what we see is that other people are trying to use battery systems actually to store the energy during the day and then to produce hydrogen overnight by just taking the hydrogen from the energy out of the batteries. I'm not sure about what's the best, and I would be certain that it is also location dependent. But when we look at, for instance, the case of Europe, I think that the infrastructure is going to play a key role in providing actually this flexibility, meaning that hydrogen pipelines are coming. You have seen, I'm sure, some of the studies of the gas TSO, so Gas for Climate Europe, actually aiming at developing infrastructure for hydrogen. And I would assume that if this is implemented, then actually you can think about having a decentralized hydrogen production injecting the hydrogen in this hydrogen backbone, and then having those industrial processes, taking the hydrogen from the infrastructure, and then you solve the, I'd say, the flexibility issue, and you really have a kind of energy storage system with hydrogen at the core.
Right.
Dennis Armin speaking here. Actually, you shared my view because you already mentioned a couple of solutions in order to get rid of these challenges. So I totally agree, but this is, you can simulate, you have some technical options. It's all about pricing and costs, right? So I guess we share the view.
No, sure. What I wanted to highlight is the role of the infrastructure, and actually the I'd say the various options which are available for the different cases that we see.
Yeah. So in other words, we can manage, right?
Right. So I guess a follow-up question: if at the scale and scope, then the cycling of the electrolyzers and things in tracking the systems is not, you don't, in the longer term, you don't see as impacting the lifetime of the electrolyzers as much, or is that not really an issue? What's your sense? In load following, does that have an impact on the long-term life cycle of the electrolyzers?
Tim, you mean steady state operation or volatile? I mean, of course, I mean, it's an electrochemical system plant, yeah? So typically, any electrochemical system would prefer steady state conditions.
You bet.
Yeah, so the more volatile, the more, I mean, steeper the ramps are, the higher the degradation is. But this is typical for many systems. So I guess we all have kind of measures to mitigate the risk. But typically, I mean, in general, you can say the electrochemical system loves continuous operation.
Right.
We
do
simply, actually, because this is important.
Right.
Maybe an additional comment on this, Tim, because in fact, all the projects that we do with the PEM technology, they are being operated in a dynamic operation, because that's what people want to do. So in fact, the degradation information that we get from those projects, it's already including a dynamic operation. And so then the question is about lifetime of the technology, etc. And I wanted to add one point, which I forgot, regarding the dynamic operation. Yes, maybe the stack itself is not that sensitive, in fact, to load variation. It's more all the components which are around the electrolyzer, all the balance of plant, I would say the utilities, which are, I would say, mechanical equipment. There are pumps, etc. They don't really like actually to have this kind of stop and go. And also you need to think about the downstream application. How much are these flexible towards the hydrogen production? And I'm thinking about compressors, for instance. And if you need to compress the hydrogen after the electrolyzer, these can be actually a bottleneck in the dynamic operation of the systems.
Okay. Ohira-san, I saw you. Do you have a quick comment? I have one more question for Jan, I hope, and then we're going to have to wrap it up. But any last comment, Ohira-san, on that?
Well, yes, and I have a comment about that. Yes, over the right, and we need a lot of data. So we Japan have to collecting the data, including the efficiency, total system efficiency, and we ready to share this information, how to improve this kind of technologies. Thank you.
Okay, great. Time is marching. I did want to just ask, there was one question for Jan, and it was a little bit unique, and I was very interested to get your views on it. If you have any experiences you can share on demand side management of isolated mini grids. I guess there's often isolated mini grids get overloaded relatively quickly, within half a year or so, because of unexpected growth in demand, etc. Do you have any insights or experiences from an after history around that, Jan, by any chance?
Yeah, interesting question. So this is this is an interesting point. So our focus at Enapter is on the electrolyzer itself, so on the hydrogen generation. So I would say that is our main competence. And for realizing microgrids, we work together with partners. So we've actually set up a partner program where our partners will receive training on our machines, will be very familiar with how to implement them in their projects around the world, and they will then also be able, and they are also able to dimension these microgrids, dimension these projects in the right way. So our primary way of handling those projects is through our partners. We don't do those microgrids directly ourselves.
Okay.
However, what we do have is our energy management software-based solutions. So straight from the beginning, data and data collection of our electrolyzers is, we knew this is absolutely key, especially if we were managing them all around the world. So we started with setting up a very robust software solution to monitor and control electrolyzers in any kind of configuration around the world. And in our energy management system, we operate with these universal communication modules that we developed that interface with any kind of industrial communication protocols. So this makes it very easy for our partners to build up these energy systems and manage these microgrids in a useful way, because it is by default, for example, you can very easily connect power meters, you can very easily connect to fuel cells, battery management system, PV inverters. All of this data can be combined. We can and then develop very simply these strategies and the rules to automatically control the electrolyzers and the other equipment in the microgrid to operate in a smart and efficient way. And so through this software, this flexible software that can interface with any kind of sensors and industrial communication device, communication protocols, this is what enables smart microgrid control. And so with these tools, it's possible.
Okay, that's great. That's good. I'm sorry, we're running out of time. There's a lot more questions here and a lot more information I'm sure you'd love to share and we'd like to hear, but unfortunately time has caught up with us. So with that, I would like to thank Armin. Thank you, Ohira-san, Torsten, Denny, and Jan. Thank you all very much for this very interesting panel on electrolyzer production. And I wish you all a good morning, good afternoon, and good evening. I understand there will be a short pause before we move to our second panel. And with that, thank you very much.
Thank you, Tim. Thank you.
Thank you very much.
Thank you.
Well, thank you. Oops, apologies. Thank you very much, Tim. Always a frustration when you have a fantastic discussion like that, that we have to cut it short, but I'm sure there'll be other opportunities for us to continue in that vein. We are going to have a short break. Let me just say a couple of things in reaction to what we just heard, and then we'll have a break for about, let's say, maximum of 2 minutes, just whilst we make sure that our next speakers and panels are there, and then we'll be back with you. But what I wanted to say in reaction to that discussion, so the whole goal of this Innovation Week is about showcasing innovative solutions from around the world that are enabling us to make major strides in the energy system. And I really feel that what we heard there from the panel demonstrated that. We heard some excellent examples of innovative approaches, new designs that are enhancing electrolyzers, addressing some of the performance improvements, and crucially driving down on those costs. And we also then explored some of the implications of that, some fascinating details in there that we've captured. I thought it was notable, there seems to have a shared common understanding of some of the issues that we're trying to tackle, but there's also a variety of approaches there, and that's how it should be. But overall, I felt that was very encouraging. We have many of the solutions that we need. We're developing the remainder, and overall the picture looks positive. So in our next session, in our next panel rather, we are going to build on the discussions that we had on the production of hydrogen there, and we touched a little bit on that. So hydrogen is an appropriate fuel in many circumstances, but there are some applications where it is not appropriate in its native form. So that's where the role of efuels produced from hydrogen could come into play. And that's what our next panel is going to talk about. We'll have a scene setter presentation in a moment, and then we will delve into that panel. So let's just pause now for about, let's say, 2 minutes tops. Grab a coffee if you need to, and we'll reconvene in 2 minutes' time, and we'll start with our next presenter. Thank you. Coffee, but I hope you're still with us. So we want to maintain the momentum, so let's move on into our next scene setting presentation. So we are very pleased to be joined by Michaela Azalbert, who is Chief Executive Officer of the Hydrogen Business Unit of Organised. She's also here representing the Hydrogen Council, and in her presentation she's going to talk a little bit about the work of the Hydrogen Council and its members and some examples from around the world before we dive into that second panel discussion. So, Michaela, if you're there. We can have Michaela join us in just a moment. Okay, let's just pause a second whilst we make sure we get Michaela on the line with the camera on.
Hello, do you hear me?
We do, excellent, thank you. And we can see you too, so that's brilliant. So, Michaela, let me hand over to you, and please, very keen to hear your thoughts.
Okay, thank you. Maybe first of all, to start with, I would like to thank you today, dear IRENA members and dear participants, for welcoming me for the second time for this kind of conference. Last year it was in Abu Dhabi, and I hope that next year it will be also a physical meeting. My name is Michelle Azalbert. I am the CEO of the Renewable Hydrogen Business Unit within ENGIE. It has been created 3 years ago. And today I will represent the Hydrogen Council, and I will also take my ENGIE hat when I will showcase to you some of our concrete projects. So the objective of my presentation today is to share with you what potential we see for the synthetic fuel, the efuels, and for renewable and low carbon ammonia more specifically. Next slide, please. So to start with, next slide, please. To start with, maybe a few words about the Hydrogen Council. It has been launched at the World Economic Forum in 2017 in Davos with 13 members. And the coalition currently consists of 92 members, which collectively represent total revenues of 19 trillion of euros and close to over 6.5 million jobs around the world. It is the first global initiative of this kind, and the objective of the Hydrogen Council is to position hydrogen among the key solutions to transition toward a low-carbon economy. And to achieve this goal, the Hydrogen Council works with and provide recommendation to key stakeholders worldwide, such as policymakers, investors, international agencies, and civil society. The Council sees hydrogen as an enabler of the future energy system and growing its role over time in delivering tangible benefit. Next slide, please. So 90 members from 92 members from 18 countries all across the value chain. Next slide, please. Next one, please. The Hydrogen Council has the ambition to first accelerate their significant investment in the development and the commercialization of the hydrogen and fuel cell sectors. Second, gather actors along the value chain to ensure industrial development of key components and comprehensive deployment of renewable and low carbon solutions based on hydrogen, while increasing at the same time visibility of existing hydrogen solutions and the progress being made in the sector. Third, provide recommendation and encourage key stakeholders such as policymakers, business community, and also international agencies and civil society to increase their backing of renewable and low carbon hydrogen as part of the future energy mix with appropriate policies and supporting schemes. And lastly, advocate for the important role of renewable and low carbon hydrogen technologies in helping to meet climate goals, energy security and competitive targets. Next slide. Our vision is that hydrogen has a key role to play in the energy transition, and based on an in-depth analysis of real data, industry data, we estimate that cost will sharply fall by 2030, thanks to the scale-up, making hydrogen a competitive low-carbon solution for 22 applications and addressing 15% of global energy demand. By 2050, hydrogen reaches its full potential, delivering 6 gigatons of CO2 abatement annually and 30 million jobs. So the second part of my presentation is to share with you what potential we see for e-fuels and more specifically for ammonia. So ammonia is today mainly used for fertilizer production. It's a first activable segment where the competitiveness gap between hydrogen-based ammonia, renewable hydrogen-based ammonia, and fossil gas-based ammonia is the lowest. So it's a low-hanging fruit in terms of decarbonation. It does not require also to change the production of the ammonia, the process of production of the ammonia, which consists in capturing nitrogen and combining it with H2 through the Haber-Bosch process. Today, some figures: half of the 70 million tons of hydrogen produced on an annual basis is used as a feedstock for the production of fertilizer, mainly for the production of ammonia, and also the rest is used by refinery for the production of biofuels and methanol and also other processes. So today, ammonia is a significant market on its own, and it will continue to grow at a rate of around 2 to 3% per annum, according to the experts. Most part of the ammonia produced is used by the fertilizers for fertilizer production, around 80 to 90%. And the remainder is used for the production of explosives and also other chemicals like refrigerant, cleanser, textile, resins, and so on. Next slide, please. Maybe just in a few seconds. And in addition to that, to the fertilizer sector, ammonia can also be a fuel, a clean fuel for the local cogeneration or also coal plant, whereby you can inject directly ammonia into the coal plant and produce electricity. And it can also be a fuel for mobility, thanks to ammonia fuel cells, and to be also a clean fuel for mobility and especially for heavy-duty mobility. Next slide. So beyond just ammonia, e-fuels will contribute to decarbonize mobility and especially heavy-duty mobility. Why so? Because batteries are not today the solution, mainly for autonomy and weight reasons. E-fuel entail a wide range of zero carbon or low carbon fuels, like gaseous H2, liquid H2, synthetic gas, renewable ammonia, e-methanol, e-LNG, so, and also e-kerosene. And they address different types of heavy-duty mobility, road mobility, shipping, aviation, and rail. To note today that within existing port facility, within 120 ports, you already have ammonia trading facilities. So you can have directly access to that. In addition, so to the potential of the fertilizer market, taking into account the potential of the mobility, heavy-duty mobility market, some experts consider that the ammonia production could increase by 30% for the shipping market, which represents 150 million tons per annum. And it could also develop for energy uses and leading to an ammonia market of 430 million tons in the long run. This is to say 2.4 times more compared to what it is today. As regard NG, we are active on different types of e-fuels through very concrete projects implemented right now. For instance, in a gaseous renewable hydrogen for mobility, the Zero Emission Valley project in the southeast of France, which consists in 20 refueling stations fueled by renewable hydrogen. Another project which has just started with IRENA Group, the objective of NG and IRENA is to develop and to scale up liquefaction technology in order to draw the cost of the solution now down and to make it available for the shipping market and then also for the aviation market. We have also a project around e-methanol as a fuel in Belgium, in the port of Antwerp. It's a more demonstration project, and we will produce synthetic gas by the combination of wasted CO2 and the production of green hydrogen through electrolysis. And last example, it's about train. We have, together with partners, among other Alstom and the Groningen province, tested during the first quarter of this year a solution based on renewable hydrogen for trains. And we tested it over 55 kilometers with seven refuelings done during that period. And it went pretty well. And now the next step is to then deploy at a larger scale this solution, and the province of Groningen will engage into that. Next slide, please. In the long run, we will export renewable resources from countries having massive excess of renewable energies to countries that will not have enough to meet their domestic demand. And today, there are different options available. As an energy vector, hydrogen can be transported over long distances through liquefied hydrogen or different forms of hydrogen carriers, such as ammonia again, methanol, formic acid, synthetic natural gas, or liquid organic hydrogen carriers. And some of them, such as synthetic gas or ammonia, can rely on existing infrastructures. Next slide, please. So maybe a few words about a concrete project we have today in the portfolio within NG. One example around e-methanol. So the purpose of this project, which is already developed for the first step with a design already achieved. It's about the production of e-methanol in the north of the Netherlands, in the Groningen region, on our plant in Groningen, Hemshaven. This is an industrial scale project developed in 3 phases, and the first one is about 100 of megawatts. And the product will be first used in the chemical area nearby. But this project is at the corridor of the European Hydrogen Valley, and then it can distribute renewable hydrogen in the nearby countries. A second project, next slide, please, about ammonia. It's again an industrial scale ammonia production project based on renewable hydrogen and dedicated in the first step to fertilizer production of zero carbon ammonia. Again, it's a project in gigawatt scale developed in 3 phases and starting with a double-digit phase. Again, the design is ready, and we have developed it together with Yara in Australia. And it's exactly what has been said in the previous panel session. It's about finding the right design and the right optimized design, whereby you minimize the total capex of the solution, capital expenditures, linked be it to the production of renewable, to the storage of renewable electricity, to the storage of hydrogen, and also to the distribution of hydrogen. And at the end of the day is to find the right design that will lower the cost of the total solution, but also will provide a reliable solution. And it's about also flexibilizing the downstream process of Yara, extracting some flexibility in order to reduce the total cost of the solution. And lastly, as being said previously, it's about energy management in order to optimize any excess of renewable energy or any shortfall of renewable energy. So it's all about that. So it's about integration, but it's also about development and establishing the business case, whereby you not only have the long-term offtake, you not only have the technical solution, but you also have the subsidies that will help the project to take investment decision right now, because the product compared to fossil, the fossil product is more costly. Next slide, please. So there is today a scientific consensus on the reduction of renewable H2 production cost. And renewable H2 should be competitive with grey hydrogen by 2030 in the best geographies. However, green H2 production comes at a higher initial cost than its fossil equivalent. So we face this competitiveness gap compared to the alternative fossil solution. So we need today a supporting scheme in order to trigger this cost decrease and to bridge the competitiveness gap in the early years. So we believe within the Hydrogen Council that we need policies to support the development, the takeoff of renewable hydrogen, and that they rely on 3 main pillars. The first one is on the supply side, to provide subsidies or set up contract for difference mechanism to offset on a temporary basis this competitiveness gap. Second pillar is on the demand side, to set short-term and medium-term quantified targets for industry, transport, to stimulate also via public tenders the demand. And the last pillar is about developing a roadmap of decarbonation of the energy system, followed by concrete action, such as implementing a traceability system like guarantee of origin, distinguish also renewable hydrogen from a low-carbon hydrogen to give the chances to the two products in parallel, and also to implement storage obligation because the system will require this kind of flexibility solution. So to conclude, my last words, so we need to invest and to elaborate and to implement now the required supporting scheme in order to enable a hydrogen solution to provide competitive, adapted solution by 2030, and in order to fully unlock the potential of renewable hydrogen. We must say that today a certain number of countries have already announced very ambitious targets and also designed some support plans. If this is the case of European Union, Germany, France, Portugal, Korea, Japan, Australia, and we hope for other countries also to follow. However, beyond specific plan, this is important that they are implemented now, that they materialize now, because we need to take now the investment decision in order to develop and to implement the ambition in terms of installed capacity, and also in order to deliver with regard to the Paris climate goals. Second, action and effort should be collective at international, at regional, at national levels by all stakeholders. And synchronicity around the action of all stakeholders is very important in order to speed up. And also we need international coordination to ensure harmonization of regulation and standards, including safety, which is very important. So the cost difference will only be temporarily, provided that the investments are made today on a significant scale, and that they receive the necessary support, legislative, regulatory, and financial to allow this deployment. The industry is ready, and we can together act now. Thank you for your attention.
Thank you very much, Michelle. I thought that was an excellent scene-setting presentation, really teases up nicely for the discussion that is about to follow. You highlighted some really interesting examples there, which I think are very encouraging, and we certainly very much agree with your final messages there about the need for action and crucially the urgency of that action now if we can have the solutions we need to scale up in the 2040s and 2050s. So I think that teases up nicely for our next panel. If I could ask our panelists to turn their cameras on, allow me to introduce Fernando Gomez. Fernando is from the World Economic Forum, where he is head of chemical and advanced materials for industry. Fernando, I'll hand over to you to introduce your distinguished panel. Thank you.
Thank you, Paul. I want to make sure before I carry on that you can hear me well. Am I good to go?
Yes.
Thank you so much. And thanks to IRENA for this invitation. It's a pleasure to moderate this discussion, where we're going to focus on basically the continuation once we have hydrogen. And I think it's in the minds of many, this is the moment to really explore the versatility of hydrogen, not only as a direct fuel, but pretty much as a platform for so many applications in the energy space. I'm happy to host a very interesting, knowledgeable group of panelists. You'll see them on the screen. Badr Ekin, who is the Director General of IRENA in Morocco. Kilian Krohn, who is with DINA, the German Energy Agency. Karen Braga with ThyssenKrupp, joining us from Australia. And Dan Fellman, who's a partner with Sherman & Sterling. What we would love to do in this session before I hand over to the panelists is three things. One, take a look at the current technology landscape. Every time that we explore the opportunities with hydrogen and basically the e-fuels and carriers, there are lots of questions about the current state of technology, and that's one area that we'd love to basically sample from the practices that our panelists are leading. So the first part would be on the technology landscape. We'd love to spend some time talking about the enablers. What is necessary to really achieve the scale and to deploy hydrogen, ammonia, and other e-fuels at the scales that are going to be necessary in the future energy mix. And I'm sure that especially with the Q&A part, we're going to spend some time on those challenges and those roadblocks that perhaps we need to pay some attention to getting out of the way. With that, before I turn to the panelists, thank you very much for the invitation. And I want to just position us in two birthplaces. One is very happy to have seen the birthplace of the Hydrogen Council, and thank you, Michelle, for that introduction in Davos at the annual meeting of the World Economic Forum. This is definitely a sign of where we are with hydrogen. The renewed interest, the greatest commitments of so many companies, and now being matched by so many expressions at the National Strategy Declaration. So hopefully we're having this dialogue in a very good moment, looking into the future. And the second is, as a chemist, inevitable to think of the birth moment of the modern industrial chemistry and chemical industry, which was making ammonia. So very excited to hold this, and I want to I would like to start actually with Kilian in this discussion, and turn to you, Kilian, for your remarks. Give us a sense of where we are in terms of the technology, and we'll come back to Bader as it is in this screen.
Thank you, Fernando. Now I see we have to switch the slides shortly. So happy to be here. We as the German Energy Agency maybe use that time for a little introduction, work always at the interface of policy and together with private and public sectors. So we have a variety of projects going on. I'll present predominantly from a project, an initiative that we launched in 2018 called the Global Alliance Power Fuels, where we look at hydrogen and hydrogen derivatives and what their role is in the global energy system. So talking about scaling power fuels and jumping right into the next slides, I'll just link up to the discussion that was presented by Michele earlier on. What are we talking about when considering fuels and also chemicals in a sense, or energy carriers more broadly from renewable power? That obviously always starts with electrolysis, but then can get a bit confusing and complicated, and that's why I listed here what we see are the main processes in conversion. That would be methanization of hydrogen and making synthetic natural gas from it, Fischer-Tropsch processes and methanol synthesis as the most important ones to derive liquid hydrocarbons that could essentially replace most of the current applications for crude oil-based products, and then ammonia synthesis that also Michele touched upon earlier on. Now the question arises, which of these fuels will play which role in the future, and also more importantly, where can we get the carbon from that we would need for those synthesis steps? And the nitrogen, it's a bit easier, but for carbon, it is a tricky question that I think we will touch upon the panel. Maybe the last point regarding this slide, we really see power fuels, as we call them, or efuels, as a solution in almost all sectors of the economy and of the energy system to different degrees. I brought with me for a bit more detail the next slide. If you could switch, please. And we ran a study, that we are about to publish on a 100% renewable energy system in 2050. And many of you will say now, okay, 100% renewable in 2050, is this really necessary or realistic? It's a bit of an exploratory scenario where we just trace being in line with the Paris Agreement. What would that mean in terms of transition for the global energy system? What we find there is, unsurprisingly, a declining overall fuel demand due to heavy electrification in as much as we can sectors in the energy system, especially transport, something, and so on. But we also see that there will be a significant global demand for electricity-based fuels. And on the left, you see biofossil and synthetic or e-fuel global demand combined. On the right, you see the synthetic global demand, and you see the 2050 bar is not much different for both. So that means with zero fossil fuels and all the biofuels we can sustainably produce, the rest will have to be filled by electricity-based fuels. And there we see really a whole bunch of fuels, that is methanol, ammonia, liquid hydrocarbons, methane, and hydrogen. So hydrogen being one of them, but methane playing a role in parts of the heating sector and some remaining applications, liquid hydrocarbons playing a role in aviation and marine sectors predominantly, methanol and ammonia predominantly as a base chemical replacing current petrochemical production. So we see exponential growth if we're really serious about 100% renewable energy system. On the next slide, we also analyzed what that would mean for global trade. Because yesterday I was on a panel discussion and some of the speakers said, well, hydrogen would be the new oil. But for it to actually become the new oil, the key component that we are lacking is tradability. Tradability works best with liquids. It does work with hydrogen to some extent, but it's just way more complicated. We analyzed in this study, it's the same study that's forthcoming very soon, who would actually trade and why would they trade and how much would they trade, we see that especially Europe stands to benefit strongly from the import of liquid power fuels from other world regions that have lower levelized costs of producing power fuels, and other regions, especially Sub-Saharan Africa and South America, could benefit as main exporters. I think that is not surprising looking at levelized cost, but it is maybe a bit more surprising that other world regions have less of an incentive to do so. Now, finally, on the next slide, what does this mean for innovation? And I didn't want to overcomplicate things here, so just 2 short points. What's the role of innovation on technology? I think we've heard in the previous session that hydrogen electrolyzer technologies stand ready to be scaled at industrialized scale. And I can say for most of the other synthesis steps that I just presented to you, they are commercially available, sometimes since decades or centuries, to be bought from equipment manufacturers. So most processes are proven and they're commercially available. The only exception being a direct air capture of CO2 from the atmosphere, something that is currently being tested and demoed, and some new synthesis routes that provide or potentially provide efficiency gain. However, process integration matters. That's what we also saw for the electrolyzer discussion earlier on. But R&D is to play a smaller role in this scaling up that we are discussing at this session. So technology may be a bit less important than the other point. That would be policy innovation, not in the sense that we don't know how to give the right incentives, but that we actually get into doing. And we know from our discussions with private sector stakeholders, they need targeted regulatory support. That could be offtake schemes. That would be the ideal and easy solution. For example, contracts for difference. There could be fuel quotas or the ability to fulfill other kinds of mandates and obligations through power fuels. And that is currently debated in the RED II, which was already part of the earlier discussion. In the long run, I would see this technology to become competitive with other abatement options. Competitive by decreasing cost, but also competitive by the rising costs and credits you get in market-based measures such as low carbon fuel standard in California, border carbon adjustments, emissions trading schemes, and carbon taxes elsewhere. So I think we are really a bit in a gap right now between early commercialization and long run competitiveness, and let's try to address this funding gap together. Now, thank you for that, and for your attention. On my last slide, just some contact details, please do get in touch. We are working with a range of private sector stakeholders here and also looking forward to expand this network. Thank you, Fernando.
Thank you, Kilian and team for the flexibility. This as an introduction has been quite good to show the broader landscape. Just a reminder to all participants and those who are right now attending the session, we're going to be doing questions through the Q&A box. So we're going to probably accumulate for all speakers. I'm going to turn right into Badr, just picking on one of the elements that Kilian suggested there, which is the policy side. And we've always heard that the technological development without the right financing and policy innovation, it's the sound of one hand clapping. And I think what we're seeing now is a number of policy moves and policy interventions, but also this combination of public and private and largely governments leading. So I'm happy to welcome Badr to share his perspectives and from the perspective of IRENA in Morocco, not only research, but also very tightly working with the plans of a region that is going to be increasingly important at this intersection of solar and hydrogen. So Badr, welcome.
Thank you very much, Fernando, for the kind introduction. I would like as well to thank Kilian because he introduced as well a bit my presentation. I'm very glad to attend today as a potential exporter of efuels in a few years. Thank you very much as well for IRENA for the kind invitation. First of all, I would like to introduce a bit the Moroccan context. I will as well at the end take the opportunity to comment what Fernando said regarding, and as well Kilian, regarding the regulatory innovation as well as the role of the technology, and then to have this balance and what we would like to develop in our country, especially after an ambitious program and successful deployment of solar energy. But I think there are a lot of things what we have to optimize. Next slide, please. I would like to introduce briefly IRENA, the institution which I am in charge of. We are developing R&D, applied R&D infrastructures. We are a little bit like the Fraunhofer Society, and we have as well a funding agency for collaborative projects, and we will launch by the beginning of next year in January call for proposals with different partners and countries, like for example Spain, especially for topics like hydrogen and e-fuels, and we are as well hoping to do the same with Germany, and we're in discussion phases to be able as well to launch joint calls to develop demonstration and pilot projects. Next slide, please. As I said at the beginning, and maybe as you know, we are deploying a lot of renewable energy power plants, wind energy, as well as solar energy. We started with CSP, with concentrated solar power, and now slowly we are developing hybrid power plants including PV and CSP. And I think in the next months, we will see as well hybrid power plants, wind power and photovoltaics. We have an important renewable energy resources. We have load factors regarding wind energy up to 70%. And you followed as well in the last months, we signed an agreement with Germany regarding the cooperation in the framework of the energy partnership, but especially, of course, then for hydrogen. Next slide, please. Morocco was identified as one of the countries with an important potential to be an exporter of green hydrogen or other green derivatives. And if you might then click on the slide, and there are as well a study which identify Morocco could cap up to 4%. There are as well other studies which speak about an 8% of the global power to X market. And then what we did to prepare our strategy, next slide please. We conducted different studies. We conducted with partners technology studies to have an overview about the maturity of the different technologies. We spoke before about then the electrolysers. We spoke about then now the some proven technologies regarding the megawatt scales. We have as well then to know about technological roadmap if we have then to go then to the gigawatt then scale, but as well regarding the synthesis and then so on. It was very important to have this technology study as well as a study for the potential and the kind of a social economic study for Morocco. Last year we set up our energy minister set up a national commission for hydrogen, and we will publish before the end of this year our hydrogen strategy. And I said it then before, we had as well then the with this signing of the agreement with Germany. Next slide, please. Another click, please. Thank you. Those are some first results, insights about then the Moroccan strategy. regarding power to X. It's clear that for the short term, ammonia will play an important role. Why? Because we have a very important fertilizer industry in our country. We are one of the most important exporter of phosphates and as well of different derivatives of phosphates. And ammonia will play an important role because today we are importing every year around about 2 million tons of ammonia. It means we might be then able to produce by our own this ammonia, and then later on to use all the existing facilities to export as well then ammonia. Other efuels will play, and then we have it as well in one study which is now conducted by Frontier Economics, and we're identifying as well a potential to be able as well to export other synthetic fuels, but not for the domestic use or need, but more than for the export. Next slide, please. Next click, thank you. And this is what I was then saying as well for the other sectors. For Morocco, we expect to have as well the development of ammonia, of course, and green ammonia as well, maybe then green methanol, and then later on as well other synthetic fuels like synthetic kerosene, synthetic diesel, but maybe more for the export. Next slide, please. This is what I was then saying. It means that the projections for 2030, 2040 regarding the renewable energy installed capacities for 2030 might be up to 20 gigawatt. This is an example to have 50% of wind power, 50% of PV. 2040, it might be as well up to 60 gigawatts, and for 2050, up to more than 100 gigawatt installed capacity, to be able then to produce our need regarding then ammonia, as well as to be able to export and then to be an exporter for partners like, for example, Germany, other European countries. Next slide, please. And this is why in our strategy regarding the R&D platforms, we are now preparing one new R&D platform in the middle called the Green H2A, green hydrogen and applications. At the beginning, we spoke about green hydrogen and ammonia. Now we're speaking about green hydrogen and application. Next slide, please. And the idea, of course, is to have them different steps. And then this R&D platform, the Green H2A, in the middle will integrate different pilot projects. We are now in the selection phases for a partner, for an industrial partner, to develop then this facility with different projects. I will then give some information in the next slide about then those projects. But here it's important to say that we will have then a range of 5 megawatts regarding the production of green ammonia using different electrolysers, as well as then the ammonia synthesis and production and power to liquid, production of synthetic kerosene and synthetic diesel. And then this would be then, it will start by the beginning of 2021. 2022 in Morocco, we will launch then a reference project. It might be then a capacity of 100 megawatts, and normally the target is then to have it by 2024 to have then the commercial use, as well as to be able to use it in the industry. Next slide, please. Yeah, and here this is the structure of the Green H2A, as I said, different than electrolysers, as well as power to liquid. And the idea regarding this R&D platform and the call for proposals to be able then to fund different pilot and demonstration projects. The use of ammonia for other applications, not only then for the fertilizer industry, the use as well and the production of other e-fuels. Next slide, please. And this is then the last slide, I guess. Yeah, and the idea, of course, and is to develop, and this is what we would like them to do with our partners, to have development of a regional clean energy union but to be able then to develop an ecosystem together jointly, and to have as well a development of an industrial regional cluster. We saw in the past, and this is maybe then one of my last comments regarding the solar energy, this is a little bit then strange that even if we have more than 600 million Africans without access to electricity, it means there is a huge potential for PV. And then even if it's the case, we saw a lot of companies in Europe going then bankruptcy. I think regarding then the hydrogen strategy, regarding Power to X, we have then to work together, and I hope as well that European countries will collaborate together. Last slide, of course, I have to thank you, and I wanted to take the opportunity to invite you to our World PTX Summit in December. This will then take place partly physically and partly virtually. Thank you very much for your kind attention.
Thank you, Badr, for that. I'm sure that your illustration is going to generate a number of questions. I have a few myself, but again, an invitation to all participating in the session to put your questions in Q&A. Quite interesting perspective. We've talked about the versatility of hydrogen, and naturally the question is, how do we make sure that going through that phase of integration and deploying the right infrastructure is not the break of this path of integration. So I'd like to turn to Karen. Good afternoon, I think good evening in Australia, and hear your perspective from ThyssenKrupp as a provider and developer and the forefront of a lot of the technologies, the infrastructure and equipment perspective that are going to be needed to make to hit those goals in 2050. So Karen, thank you and welcome.
Thank you, Fernando. Thanks for a very warm introduction, and also I think a good lead into the topics that I will briefly touch on today. As the title of my remarks suggests here, that we'll elaborate about 3 different elements of P2X, and we will look at quickly first why e-fuels and what future they hold in our futures essentially. What are the challenges to implementing the Power-to-X? And then what we at ThyssenKrupp are doing about it, and how these solutions are basically being turned into our technology DNA. I guess all of this in perspective of a place which is quite ripe for a large-scale export, which is Australia, and that's why I'm here today. And thanks, Badr, before you kindly shared the study where it shows Australia as a giant. Nevertheless, we have a huge potential, and where these large-scale technologies. Yeah, thank you, Fernando. Okay, so in this slide, just touching base on exactly why we need e-fuels, what value they hold in our futures. So as you can see, this is from an IEA report published. Even by 2050, the energy mix scenario indicates that there will be a need for fuels in areas which can't be electrified. So they're hard to abate sectors, aviation, mobility of some of the heavy haulage mobility, mining, etc., and plus also lots of industrial uses. You just simply can't electrify them. So there will be need to replace, I guess, the existing fossil fuel energy sources with green molecules, and converted from renewable sources, no doubt. So why are they not currently deployed in full scale? So there are economic barriers that exist, and we talked about a lot in the previous session as to what they may be. Electrolyzer scale in particular was one of the main reasons quoted, and I think we're all very well aware of the way industry is heading. We as a quite a large scale electrolyzer supplier also totally agree with the sentiment and the comments made in the previous sessions. And the only way to reduce the cost here is by scale up, large scale. So I won't touch base too much on the first point. It's quite clear, but the second one maybe is of more of interest, which is the intermittency. So that's a challenge that we heard about it just before in previous sessions. Our very knowledgeable panelists talking about it. What exactly intermittency does to PTX value chains. So I think that's briefly what I will touch on today, and lead on to how we overcome those challenges. So effectively, the intermittency results in low conversion of electrons to chemicals. That's, I think it's all but fairly obvious. And then also results in underutilization of the plant because of the intermittency. It's not steady, obviously, in nature of the energy supply. So by way of designing or making sure that you grab everything that is being generated, or most of it economically, you end up oversizing the plant in most cases. So let's take a quick look at some of the challenges related to intermittency. Next slide, please. Okay, so on this slide you see here is the key theme here being I think the one word that is synonymous with the renewable power generation is randomness. You know, in other words, I'd call it entropy, both the thermodynamic and system entropy, right? So it's the causes of all the headaches. Needless to say that. So different renewable power generation mechanisms. I haven't shown hydro here, for example, but PV and wind, perhaps the two main ones, have different fingerprint, or as I like to call it, the actual characteristics of the sources of the generation. So essentially, with all that randomness being introduced into the system, it gets imposed on the very first part of the value chain, or the critical part of the value chain, and this in this case is electrolysis. So we heard about that as well previously, that electrolysis obviously has to sing and dance accordingly to the energy supply from the renewables. And that essentially creates a different harmonics of the randomness. And then you've got hydrogen storage, obviously, to even everything out, because our last technology block, which is the chemicals conversion, does like to run in steady state. You know, as much as electrochemistry likes to be at steady states, catalytic chemical reactions even more so. So how do we take all of that that's so random and turn it into something that is steady, and still come out at the other end with a unique, I guess, and a credible business case? So that's the challenge. And perhaps in our view, there are two-pronged approach, right? So it's just like with any other thermodynamic system. It's a case of minimizing the introduction of randomness, or entropy in this case. And then once it's in there, to then mitigate it. Right? So there are the two pathways. On the left side of the slide, you see perhaps the how to minimize the randomness or the intermittency in the first place. So obviously that comes with the right scale. So there was a remark made in the previous panel that obviously scale will help. We in Australia have done several case studies, and we can vouch for that quantitatively. That you see that down there is a graph which shows the intermittent behavior of a large-scale PV. That's a 200 megawatt. That's only a 200 megawatt system, and we're talking gigawatts here. What you see here is the clusters, the small clusters, which are in the blue lines, display, and that's a 3 megawatt cluster, display some degree of randomness. So this is on a tropical day. The gray lines in the background are the GHI, or the irregularly fluctuating, you know. The y-axis is the percentage per second. However, the red is essentially your output from the large-scale 200 megawatt plant. So it is flat as. What you can see here is that the system, or the thinking, or the approach that might apply to a small-scale P2X plant, which are demos, cannot be simply translated to a large-scale plant. You know, it needs a horses for courses approach, and hence such. A really good, I guess, a big caution against overcompensation by investing in, you know, technologies or I guess the systems which might we might be trying to abate something that doesn't exist. You know, it's like fighting a ghost. It isn't there. So on the right hand side, you see the graph that as the PV scale goes up, the randomness does decrease. However, put that into perspective of the full chemical value chain. So this is all well and good that in power generation, it's very easy that, you know, to show something like this. But what it means for chemicals when you convert those electrons into chemicals, starting from electrolysis onwards. On the right-hand side of this slide, you see the couple of probability distribution curves, and they effectively come out from two different scales. And I have them in there because in order to show why, again, it needs a thought-after approach. The top one is actually from a small scale. You see that there is, on the y-axis, essentially shows a large percentage of time whereby the plant is actually running at below turndown, or perhaps outputting power that's not enough to feed the chemical plant downstream, be it ammonia or methanol. The chart below, it shows the opposite. It's for a very large scale plant, and there you see that the turndown percentage is quite low. And so how do we manipulate all of this, right? So essentially in a greenfield facility, it starts with, okay, scale's our friend, that's helped minimize the intermittency. But then we come to the appropriate mix of wind and solar, or the mix of the energy sources. Yeah, so such that the downstream plant then actually there is less exposure to the intermittency. Right, so all of this essentially passes one message. You go from left to right in this, and one of the things that becomes very obvious and evident here is that if you can control all the key technology elements that you can manipulate, that you can develop coincidentally for a particular outcome, that you can unlock a lot of value. And why I say that is because that's exactly what ThyssenKrupp does. Yeah, and you saw the first slides in there. We are quite, I would say, lucky in that sense that we have control of the technology base, the way we develop it from left to right, all the way from electrolysis to the chemical plants. And that's our technology DNA. And with doing that, we have created complementary technologies which are fit for systems. They are being both looked at a system level to integrate, as well as at a technology level to make them flexible, but also to minimize the need to be flexible in the first place. Yeah, that's very important. Next slide, please.
We've got about a minute of your presentation.
Yeah, no worries. It will only take a minute. So that's essentially shown in the next slide. Again, this is something that we do all the time in every time for every project, for every customer that would like a full-scale end-to-end facility. It's a matter of looking at all the value unlocking facilities and essentially coming up with a concept that delivers the best economic value. Next slide, please. And together with a very large-scale portfolio of key equipment, such as electrolysis, this is our, you can see the 20 megawatt plant there, 4,000 normal meter cube an hour, flexible, purpose-built to sit on the back of a chemical facility. That's the key point here. We are ready in this sense. And then together, last slide, please. For how this actually balances or sits on the back of the large-scale chemical facilities. So here too, we have concepts for ammonia, referenced capacities. The largest plants ever built in the world today are ThyssenKrupp's, over 3,300 tons a day. For ammonia plants, we have capacities available from 50 to 5,000 tons a day in single train. Yeah. And with that, we've specifically designed and developed concepts for decentralized as well as centralized applications, as well as the export grade. And that's where Australian context comes really handy, because this is what we've been working on. And these lessons learned that as to how the intermittency, et cetera, behave is what we've fed back into our technologies. On the right-hand side, similar for methanol, plants available from 10 to 2,000 tons a day, single train. And again, we have demo plants. The Carbon to Chem, one of our pilot plant facilities in Duisburg steel mill, is actually demonstrated since 2018 production of chemicals based on renewable power and carbon dioxide pulled out of the steel mill gases. So the message here is clear. It's essentially what we want to say is that there are still hurdles and challenges remain. However, smart technology, as well as having, a view on the full P2X value chain, really chips away on the economic hurdles. Yeah. So that's essentially the message I'd like to pass. Thank you, Fernando. That's great.
Thank you, and this is a very good illustration of one of those elements that has been pointed out as necessary to ensure that comprehensive evolution, which is the integration of the multiple pieces and the multiple technologies that will need to be part of a bit of a concert. I think we've heard initially from Kilian this overview and illustrating again the versatility of hydrogen, the connection to fuels and ammonia, from Badr, the role of the private sector, of the public sector, and from you, the integration. The last piece of this puzzle is basically looking at the business side, the financing of this, and a bit of the risk that is perceived as a lot of these technologies evolve. So I'm happy to welcome Dan Feldman to share his perspective. What is missing to make this work? What is on the way of really allowing this integration to take place, and especially in the front of those who are making decisions on investing in these projects? So welcome, Dan, and thanks.
Thanks. So I'm a bit of an unusual presenter on this panel in that I'm a lawyer. I'm not an engineer, I'm not a scientist, but what I'm responsible for is helping projects in this area actually happen. And what that means is the rubber hitting the road on all of the technological issues that Karen and others have mentioned around intermittency and what that means in terms of trying to get a project structured properly, as well as the fact that, as people have said currently, whilst we may all hope that one day ammonia is as tradable as oil, currently it isn't, and therefore projects getting done today at scale need to contend with the fact that there is no downstream market at the moment, and therefore they're trying to structure themselves in a way that persuades lenders and others that one day there will be a merchant market sufficient to take all of this quantity of product. And so that's going to take us into questions about how do we finance these things, how do we get them done, as well as how do we ultimately, ensure that we have projects which are sufficiently well structured in order to make the industry happen, apart from, the discussions about how it should happen by virtue of everybody's decarbonisation commitments. If you take us to the first slide, and this will show sort of why I'm here. So I'm acting for NEOM on the world's first green ammonia mega project. This is a $5 billion project taking place at the moment in Saudi Arabia, powered entirely by renewable electricity. The green ammonia from this project, and I'll get into the quantities in a moment, is going to be exported entirely to global markets for disassociation back into hydrogen and use in transportation. The joint venture is between NEOM, Air Products, and Aqua Power, and it's going to be located in a new city that's being built by NEOM on the northwest coast of Saudi Arabia. The next slide, please. So the project's going to be scheduled to be on stream in 2025. So we're talking, real time now. The project will include 4 gigawatts of renewable power from solar and wind. It will be the largest renewables project in the world. Just sort of back to that slide, sorry. 4 gigawatts of solar and wind will be the largest project. Sorry, one slide before. Thanks. The largest renewables project in the world, apart from, of course, the novelty of being the first green ammonia mega project. The electrolyser size will be 2 gigawatts, and it will produce 250,000 tonnes a year of hydrogen through the electrolyser, production of nitrogen by air separation, and ultimately 1.2 million tonnes a year of green ammonia. And all of that green ammonia is going to be off-taken under an off-take contract by Air Products and shipped around the world, where it will be, as I said, disassociated to produce hydrogen primarily for the transportation market in the first phase. Next slide, please. So what I'm looking at when I look at a project like this is essentially when you have a first-of-kind project with a new technology in a market that doesn't exist yet, lenders are not familiar with it, how are we going to get this thing done? And I think the lessons that we learn on this project and the answers that we're developing for NEOM and the joint venture partners in relation to this project are going to be the key questions and answers that all of us are going to have to answer and address when we move forward if we're going to scale up this industry. And that's why I think this is a very interesting point in the discussion today, to stop and look at what do all of these technological and market-based questions actually look like when you try to turn them into something real. And what I've done here is sort of develop 5 key questions that I think encapsulate a lot of the different issues that all of the different speakers have mentioned. The first issue is, how are we going to sell these products? At the moment, there isn't a merchant market for ammonia or green ammonia the way there is for oil. You can't just put it on a ship and sail it around the world and someone sooner or later will buy that product. You need to have a clear route to market, which means essentially, as is the case for all new industries, effectively somebody to take responsibility and underwrite the offtake of the product. So we have, as with all new industries, a sole offtaker structure likely for the hydrogen and ammonia market in the near future. But in order for the market to scale up, at what point are we going to move to that merchant model where people building a project can know and can persuade lenders that no matter what happens to a particular single offtake contract or a particular single customer, there will ultimately be a market for this product that is able to be traded, that is able to be swapped. And that's going to address some of our intermittency issues in terms of the reliability of supply from any particular plant, which goes to some of the issues that others have discussed and which I'll come to in a moment. The second question, which is related, is what do we mean by green? When we talk about green product, particularly in the case of ammonia, what do we really mean there? We know that the hydrogen itself needs to be powered by renewable power. It needs to be essentially fed and created with green electrons as the feedstock coming from renewable sources. But if we have to have green power feeding every element of the industrial process, and potentially even further than that, the buildings, green power to construct the buildings and the material used ultimately to produce the product. The greener we get, the harder it is for more projects to scale up affordably and develop this product. But at the moment, around the world, there are different definitions in the different markets of what it really means to be green ammonia. For instance, is it the case that in all markets, not only the electrons for the hydrogen have been created from renewable sources, but the electrons for the ammonia production process? If, on the other hand, you can use some carbon in the production of the ammonia, that's going to open up a lot more flexibility in terms of scaling the renewables for the electrolysis production. You won't have to scale so high as to account for ammonia and all other elements of the process. But that's going to make project more affordable. But at the moment, there's no consensus on exactly what a green product needs to look like. There are different models in different parts of the world, and there needs to be a consensus about what it means to supply someone with green ammonia from a carbon point of view. That will directly feed into the tradability of the product. It will directly feed into the capital expenditure required, and therefore will directly feed into the viability of all of these products. The other question is capital intensity. And it was interesting listening to Karen about this, because I think the size of the projects at the moment is one of the key factors that investors are looking at when they are working out whether or not this is the right place to put their capital. Because in light of the intermittency issue and the fact that you need to scale up renewables to such an extent in order to overcome the intermittency issue, at the moment, as we see it, you do need to have very large scale projects in order to have a reliable amount of ammonia to be able to sell, which would underpin a financing. So we need to have big projects, and that's going to continue to be the case until you can overcome the intermittency issue by, for instance, swapping green hydrogen forwards that are able to be predictably sold across a given year with the fact that another project might be predicting slightly less solar and wind at the same time. You might be able to offset one project's intermittency issue with another project's intermittency issue, and that would involve a sort of portfolio-based spreading of the risk across multiple different projects. And ultimately, that's what a market needs to look like in order for people to get comfortable that there will be sufficient customers for the product, irrespective of whether or not one particular project has a bit less wind this year than it might have next year. So I think scaling up at the moment, one of the chicken and egg situations we've got with these projects is that you need to be big in order to get the project financed, because that's how you minimize your intermittency. But on the other hand, the bigger the project, the fewer people have the money to do it. And so until we have a few of these projects going around, I think it's going to be difficult to overcome that intermittency issue without a very careful contractual structuring, not only at the asset level, but also in customer contracts and the extent to which customers are going to be flexible in terms of the supply of ammonia. And those are important elements of the structuring which we're currently looking at. In terms of the technology and scale up, with any new industry, whether LNG to power in recent years, chemicals before that, one of the major issues that investors and lenders have is the reliability of the technology once it's scaled up. We all know that there are many projects that have been done with a single electrolyser, and it's reliable, it's well-known technology. But ensuring that you can hook up multiple dozens, hundreds of electrolysers to a large solar and wind resource, and then hang off that an air separation unit, as well as an ammonia production unit, as well as storage facilities, as well as battery storage, all of which are necessary to get one of these projects away. That's never been done before. And so we're going to be looked at by lenders from the point of view of how do we guarantee that the projects are going to work once they get underway. And so from our point of view as lawyers, we really need to be able to sell the technology to the lenders as much as the equipment suppliers in order to persuade lenders that this is something that can be done reliably, that it isn't a scary new thing, and that hooking together these multiple different kinds of well-known technology doesn't increase the overall risk associated with the whole. And then the final thing I wanted to sort of raise to people's attention, which I think is going to be important in financing these projects, is understanding the midstream economics. So at the moment, as has been mentioned by a number of people, transporting green hydrogen itself is not feasible over long distances, and so it needs to be done with ammonia. The economics of transporting ammonia and then disassociating the hydrogen at the other end is going to be very, very important in the economic feasibility of these projects, particularly in situations where we don't yet know for sure what the markets downstream are going to look like and where the demand is going to come from. So in order to get people to commit to buy substantial amounts of green hydrogen from a project like Neoms, you need to be able to fully understand the midstream economics as well as you understand the upstream economics. And at the moment, until we have greater sense of all of the factors that are going to influence midstream economics, including in Europe, pipeline modernization in order to take hydrogen and so on, there is going to continue to be a question about what the midstream economics really look like and how they will ultimately become more and more attractive over time, and what early stage projects are going to be telling lenders and investors about. So these are just 5 questions that I really briefly, I'll wrap up now, but these are just 5 questions I really briefly wanted to mention, because these are the questions that all of the other technological and market-based issues that we've all raised ultimately feed into when you're trying to sell the story of a project in this industry going forward, particularly a large project such as Neoms. We don't have the answers to all of these yet, or at least I'm not going to be able to tell everybody what the answers are, but we are at the very forefront of financing and structuring these projects at Sherman & Sterling. In fact, we're the only international law firm with a global hydrogen team, and we are actively looking at a number of these projects around the world and really working on cutting-edge questions that we need to answer in order to get them financed and get them operating. Thanks very much, Fernando.
Thank you, Dan. We have about 9 minutes for Q&A, and I think what we've heard is a very good overview of all the different issues. There have been a couple of questions that have been put in the Q&A. I'm going to go very quickly to a couple of those, and I want to come back to all of you. What is that one thing? What is that one thing that we need to think about removing from the path to this significant scale up? But let's go to the questions in the Q&A. The first one was actually directly to Karen. Just asking for just a bit more detail on the intermittency or the stability in the megawatt versus gigawatt scale that you illustrated. So just 1 minute to address that one. We'll come back to all of you. We cannot hear you, Karen. You are on mute.
On mute. Excellent. Thank you. Thank you. I said I was going to take less than 1 minute, hopefully. The megawatt versus gigawatt, there's no real set rules. I think it really needs to be looked at for site-specific conditions, essentially. But in our experience, definitely rooftop solar or that sort of stuff, where 1 or 2 megawatt type pallets are considered, intermittency seems to be high. But as you start to get to 20 megawatt, 30 megawatt plus definitely hundreds megawatts, you're already well past the point where the economics are going to get hurt because we're going after every kilowatt hour of energy that's coming up. So I think it's from a perspective, I would say tens of megawatts versus the once you get into hundreds, definitely you're past that. From what this is what we see in Australia anyway.
Thank you for that. I'll skip the Q&A. I'm going to go very quickly with all the panelists because you've illustrated a very nice stage of the technology at this point and some moves on the policy side and basically what's coming next. Let me turn to Badr first. What is the one thing in your mind that can really unlock the potential at this stage of those technologies that are scaling up now? What's at the top of your wish list?
Yeah, I will say for the beginning to try to start with specific markets. If I take the example of Morocco, and there are of course other sites, we have to import ammonia. It means there are other costs regarding transport. There is a value regarding as well the dependency of an important then feedstock. We have maybe to start with first important derivatives of hydrogen. It means there is a need, there is a value to have a kind of to have less dependency. So, second point for me would be then the regulatory framework to develop, to have then a premium prices, to have carbon taxes. If we would like then to decarbonize specific sectors, we have to have such kind of incentives. And I will maybe then I would like to give one example. 10 years ago, when we started with CSP, with concentrated solar power, we had the cost of the levelized cost of electricity was €4 per kilowatt hour. We have today 70 euro cent. It means a multiple of six times less. I think we have enough time till 2030 to be able then to reduce the cost.
That was 3 points in your wish list. Let's try to keep it to one. Kilian, what is that one thing at the top of your wish list that is necessary?
Making it harder. So that one thing for me would be a mechanism that guarantees large-scale offtake. We have seen from Dan's presentation, if a company steps in like Apple says, well, we can do the offtake, the project comes into place. And that's what I think, or I wish for the moment as the one major thing. How exactly you design that, if that's a contract for different scheme or an offtake, remains to be seen. But just as an example, the German government in its hydrogen strategy set aside 2 billion euros for international project development in PTX and in hydrogen projects. If those projects, if that money is used as a fund to guarantee offtake, the induced investments will be much larger, and we will see actual triple megawatt class and beyond.
Very good, very clear. Thank you so much. Let's turn to Dan. You left us with 5 groups of questions, but what is that one thing in your mind that we should try to get out of the way as quickly as possible?
It's a definition of green hydrogen and green ammonia. For me, it's figuring out, aside from sort of being, I guess, completely orthodox and saying it's not green ammonia or green hydrogen unless it's 100% produced with green electrons, what is the real consensus around what is green ammonia? Once we have that, we'll be able to have projects form around that, and we'll be able to trade based on that. And I think that for me is the number one thing that's going to be important in developing the international market for green ammonia that we all need to catalyze the industry.
Okay, thanks. So better understanding and a bit of standards opportunity there. Last for Karen, then what's that one thing in your mind? And we'll come to one of the questions that's in the Q&A box. So 1 minute.
Sure, thanks, Fernando. Yeah, one thing that comes to mind, which is I think to incentivize the ready off-takers industry. Replacing the current fossil fuel generated hydrogen with renewable generated hydrogen. There's a ready market there, except that currently the economics are difficult to justify. I think if we focus on incentivizing them, that already presents a very large offtake ready.
Okay, thanks. Actually, lots of conversions there on the offtake and downstream as pulling this development. One question, inevitably, methanol and maybe the materials routes. We've heard a lot of hydrogen to ammonia and let's say the fuel routes. I'll just turn to all of you. Just is there something we need to think of maybe more actively? This is following up a question in the Q&A. Why are we not talking enough about methanol? Any concerns in your mind that we should also be actively thinking of? So just say your first name if you're going to respond to that question, as I cannot see you all on the screen.
Kilian, maybe just two short points on what may be the problem with methanol. I think from a sort of process engineering side, Karen will probably talk more about it. It's not too difficult. The challenge, two challenges I see. First of all, methanol as a chemical is a market. It's a global market. That means companies are in a global competition. That means it's much harder for regulators to come up with incentives for markets, and competition is there, so voluntary commitments I think will be difficult. Second of all is carbon source, and that was raised in the question. So where do we take the CO2 from? Karen presented the steel flue gas project there from ThyssenKrupp. That's one option. Biomass processes are another one. Direct air capture is still a couple of years away in industrial application and scaling, but I think that is one of the issues to be sorted out for all hydrocarbon power fuels as we see.
Okay. Any additional views, maybe from Karen following this one?
Yeah, sure, Fernando. I think, Kilian, you touched one point which I was going to mention, which is the source of carbon. I mean, I don't see methanol as a stepchild. I think it's undervalued. It's the simplest molecule beyond, besides methane, and I think it's underappreciated as a hydrogen carrier. But given its currently, 60% use actually going into making plastics and products, it's an automatic source of CCS. Essentially, it locks away the carbon. So the current focus is on the fuel, or marine fuel is really picking up. So from my perspective, I think methanol is underappreciated, and there's no reason why it can't. We talked in the same way as ammonia is, but we need to understand the carbon aspect, how we apply the green versus grey on carbon as well.
Okay, good. Well, with that, I think we are right on the top of the hour. So I want to say thanks to all of you for helping us build this puzzle of where we are today with not only the current state of technology, but some of the key elements that you see as potential enablers of this scale up. With that, thank you all very much.
Thank you.
Well, thank you very much, Fernando, and thank you very much to the panel. I think that was a fascinating discussion. As always, time defeated us, and would have been great to keep going longer. But we got some really great insights there. By way of wrap up, our Deputy Director of the IRENA Innovation Technology Center, Roland Roche, is going to give some closing remarks, sharing some insights from the discussions that we've had today. We're slightly over time. I hope you'll bear with us for perhaps 5, 6, 7 minutes more, just to get these sort of key points across. Let me hand over to Roland at this point, then I'll tell you about what's coming up with the rest of the week at the very end. So, Roland, if you're there.
Yes, thank you, Paul. Thanks to everybody who contributed to this very successful event. I think let's say I was very impressed by the different contributions here from different panels. I think the objective of this discussion this morning was to line out the art in innovation of hydrogen production, ammonia, and other e-fuels. And the presentations were really amazing, because I think really they were able to gather the state of the art of this new rising star hydrogen. And let's say we started with a presentation from IRENA, from Emanuele Caibi. Emanuele was very clear. The size of electrolysers are increasing continuously, bringing the total system cost down. Standardization is important to upscale from base building blocks, and thus bringing economics of scale. Projects are today already in the megawatt scale and tending towards the gigawatt scale levels. I think it was very clear in Emanuele's presentation that the capex of electrolysers to bring down the cost of electrolysers are the key for the next years. The renewable energy costs, electricity costs, are already in the right direction to support the production of hydrogen, but we also see that there will be, because of innovations, the renewable electricity costs will come down, will open the possibility towards the end of this decade to produce competitive green hydrogen. We had then a presentation from Armin Chetter from Siemens Energy, who underlined actually also the kind of initial point made by Emanuele. Important is fully integrated solution, reliable energy technology, the possibility to scale up solutions. Here also digital services are key to maintain the availability and the reliability of electrolysers, and then also, let's say, going a proven industrial scale in the electrolyzer will enable hydrogen. Then we had a very insightful presentation from Aichi Ohira from NEDO. I think he was making also the point, electrolyzer technology has to improve. He sees here a very important role for material science to develop new membranes, which he sees as a key challenge to develop further this technology. And then, let's say, the total system optimization is key for the hydrogen-related technology. Then we had a presentation by Thorsten Herbert from Nel. There, let's say, Thorsten made very clear that Nel is ready to scale up the manufacturing and is ready to quadruple the production of the production capacity for hydrogen production if the existing demand materializes and increases more. He sees here, and that was a very important point, he sees a need for hydrogen industry roadmap in Europe. He was very clear that for him, let's say, the Clean Hydrogen Alliance is working on this. But I also want to mention here, IRENA is working on a collaborative framework on green hydrogen, where we also try to discuss with policymakers and the private sector to get clarity of what will be the future of this important technology. Then we had from Dennis Thomas from Cummins, here also scalability for electrolyzer stacks is very important. The reduction of plant costs is key. Stacking efficiency improvements are needed. And he presented here a case of a product Cummins have of a pilot that is 8,000 kilogram of hydrogen production per day with a 20 megawatt system. So quite impressive. So there is already large scale hydrogen production units in place. Then also very interesting and bringing a different aspect here, Jan Justus Schmidt from Enapta. So here the different strategy instead of scaling up stacks to mass, here the strategy is to mass produce smaller units, so a completely different approach. Stacking for scale in cabinets with stack modules that can be in another concept to be combined in modules. This approach also serves the decentralization trend in the current energy system. And then, of course, we had a very interesting panel discussion on this first panel. It was very clear that hydrogen production efficiency is a very complex matter. I think there have been also questions to the audience. What was discussed was standards for comparable measurements are needed to be more clear on, let's say, how to improve hydrogen production efficiency and how to measure hydrogen production efficiency to get the clearer benchmarks here. Then it was discussed in the integration of higher shares of variable renewables, the challenge that comes from the volatility of renewables. There it was made the point that electrochemicals like continued operation, otherwise a discontinued operation may impact the lifetime of electrolysers. There the solution that was discussed was good forecasts are needed in combination of battery and hydrogen storage, and also kind of integrated systems with the current gas infrastructure may help to integrate higher shares of variable renewables and use hydrogen equipment to balance the systems. Then the second panel, equally interesting. Here the focus was on ammonia and other alternative synthetic fuels. The scene presentation was made by Michelle Atzalbert from the Hydrogen Council. She linked what is needed also to the objective of the Hydrogen Council. So very clear, unlock the scale markets for hydrogen, create business opportunities for the private sector, accelerate the investments into hydrogen, and encourage the key stakeholders in this rising technology. Also, she made some outlines of the importance of the mobility markets. I found very impressive her statements that, let's say, the current mobility sector could represent an equivalent of 2,000 gigawatt of electrolyzer capacity in the market. Also, mobility will represent 30 to 40% of the hydrogen markets in 2050. Let's say her conclusions were also very clear. Additional financial supply is needed to close the economic gap, to make hydrogen kind of progressing very fast. Also, the demand side needs to set quantified targets that the supply side can follow. Here, the proposal was also to have a road and action map to decarbonize the energy system. Then we started, moderated by Fernando Gomez, with panel 2 on ammonia and other e-fuel production. Fernando Gomez from the World Economic Forum moderated very well this very interesting panel. The first presentation came from Kilian Krone von DENA. He said all power fuels will play a dominant role in 2050. Proven and commercial technologies are already available, and process integration is, as I said also in previous presentation, process integration also for ammonia and e-fuels with hydrogen in the technology matters it is very important. On the policy side, scaling will require targeted regulatory support. And let's say the good message here that Kilian brought was the scaling will require at the beginning a regulatory support, but then in the longer run, at a later stage, the CO2 regulations will suffice to support the technology. Then we had from IRESM, Iken Badre from Morocco, very interesting insights into a pilot project and the development of a technological ecosystem based on green molecules. That was one of the very first pilots that was presented here, and it shows that a lot of things are already in place. Also then a presentation from ThyssenKrupp from Karan Baka showed a case here of a large-scale integrated power-to-X technologies with, let's say, parts of production related to renewable ammonia and also to renewable methanol. The final presentation then was on NEOM, here presented by Daniel Feldman from Sherman Sterling. NEOM is the first green ammonia mega project. Also, Daniel presented the details provided to legal and financing challenges of the project, which gives the possibility to draw conclusion what further is needed to support the important technologies. I thank everybody again. That was very insightful, top-notch innovation insights into hydrogen, e-fuels, ammonia, and methanol. I want to close here that IRENA is also working on a green methanol technology brief, which we will launch this year in November. And I wish you all a nice remaining IRENA Innovation Week 2020. And over to Paul. Thanks also to Paul for moderating and being here the master of this. Thank you very much.
Thank you very much, Roland. An excellent summary of what was a very rich 3 hours. So I think we got some key points there. Let me conclude then. We'll let you go. Thank you very much again to our panelists. You were all excellent. Very many thanks to our moderators. You were excellent too. Particular thanks to the Hydrogen Council and Michelle representing them. It was a pleasure to partner with the Hydrogen Council in the organisation of this session. We look forward to continued working together. So I hope you enjoyed this session. I hope you found it stimulating. This was session 3 of 8 in our Innovation Week. This afternoon at 5 o'clock, we will be looking at the third dimension of the supply side, looking at the role of biomass and biofuels, very much a complementary role to what we've just been hearing about hydrogen and e-fuels. So do please join us for that. You can still register at the link you see on the screen. And then tomorrow, we'll be turning our attention to the supply side. We'll start with a session on the applications of the fuels that we've been talking about today in industry. And then later in the afternoon, we'll be talking about transport. Do join us, and I look forward to speaking to you all again. Thank you very much for your attention. Goodbye.